గుర్తులేవా?
ఒకసారి టాపిక్స్ పేరు చెప్పండి.
Yeah.
అది
So,
సెమ్ ఎగ్జామ్స్ ఉండడం వల్ల కొంచెం కన్ఫ్యూజ్ అయ్యాను సార్.
okay. So till now we have discussed in the first like part simple simple mechanism. So I'm just what I'll do is I'll just recollect whatever we have discussed. Okay, then we'll
ఓకే
go because in the last class we have discussed few gate problems too, and after discussing two or three, the time is up. Today again we are going to discuss some of the gate problems. So after completing these the theory part, okay. So in simple mechanism, first we have discussed about definitions of kinematic link, okay, and different types of links or kinematic link or element, and types we have discussed. So I hope you remember the types, different types: fluid link, flexible link, and rigid link. And we have discussed those examples too. And then we have discussed about the relative motions, relative motion, and different types of relative motions we have discussed. So how many? There are three types of relative motions. One is constrained relative motion. Next is successfully constrained relative motion. And last we have discussed unsuccessfully constrained relative motion. And for this, we have given an example of a square shaft and a square hole. And here we have discussed the successfully constrained about the cylinder, piston, and the cylinder. And here we have discussed about the circular hole and the circular shaft. These are the different types of relative motions we have discussed. And next we have discussed different types of pairs. Okay, kinematic pair we have defined, and different types of kinematic pairs. So according to the nature of contact, according to the uh, nature of closure, and according to the type of contact and all those things. So first, according to the type of relative motion, under this category we have discussed so I'll discuss type of relative motion. So we have discussed the turning pairs and sliding pairs and screw pair and rolling pairs and so on and so forth. And in the next category we have discussed according to the type of contact. So in this category we have discussed three, and the first one is lower pair, next is higher pair, and next is wrapping pair. Wrapping pair comes under in kind like a higher pair category only. Okay, and next we have discussed kinematic chain. Kinematic chain. After discussing this kinematic chain, I hope you remember the definitions, right? So kinematic chain is nothing but it is a combination of pairs, but the rule is the first link needs to connect the last link, and the between the links you need to have relative motion, and these relative motions need to get constrained. Okay, these are the steps which are involved in kinematic chain. And afterwards, mechanism. Okay, just tell me when kinematic chain can become mechanism. Raghunath,
ఎస్ సార్.
when kinematic chain become mechanism. So when one link,
సార్ వన్ లింక్ ఈజ్ ఫిక్స్డ్ దెన్ ఇట్ బికమ్స్ మెకానిక్.
yeah. So the condition is if one link in a kinematic chain is fixed, then we can call it as a mechanism. Then we have discussed about meshing, and it is a combination of mechanisms or a mechanism. So for a input, we are going to get output, and then we have discussed. Ah, Chapamma.
సార్ వాస్తవిగా జాయిన్ అవుతారంట, కొంచెం యాక్సెప్ట్ చేస్తారు సార్.
Yeah, I don't have any control, ma. I think Madam is having control. Like Madam is there. Hello, do you have her number?
ఎస్ సార్.
Yeah, you can text her. I'll wait for a while. Hello, madam. రఘునాథ్ ఏమైందమ్మా, కంటిన్యూ చేయాలా? హలో హలో రఘునాథ్.
సార్ మేడంకి కాల్ చేశాను సార్, ఇప్పుడే చెప్పాను.
ఓకే ఓకే. సో
మేడం యాక్సెప్ట్ చేస్తారు.
యా యా ఓకే, నేను తను వచ్చాక స్టార్ట్ చేయాలా మరి? ఒక 2 minutes.
సార్ 2 minutes వచ్చేస్తారు.
ఓకే ఓకే రైట్.
Sir, he came.
Shall I start now?
Yes, sir.
Yes, sir.
Yeah. Okay. So I'm just recollecting, Ma. So Vasutaj, you can also just listen. So first
Okay,
we
sir.
have started discussing with simple mechanisms, and we have defined kinematic link. So kinematic link, what is the condition? It should be a rigid body such that it can transmit motion from one body to other. Okay, and we have discussed different types. And in these types, we have discussed what rigid link, and we have discussed flexible link, and the last we have discussed fluid link. Okay, these are the different types of links we have studied, and then we have went on to discuss about relative motion and the types of relative motions. We have discussed 3 types of relative motions. The first one is the constrained motion. So here you have only one relative motion with respect to the other link. Okay, and here the condition is in a system, how many links? Only 2 links will be there. So link 1 and link 2. So only 2 links. So next is successfully constrained, where the third link comes into picture to support the first and two. to have only one relative motion. And the last one we have discussed is unsuccessfully constrained motion, which we have two motions. The example is a cylindrical shaft and a cylindrical hole, where you are going to get two relative motions. One is rotary, the other is translatory. I hope you remember these things. And next, we went on to discuss about kinematic pairs. First, we have discussed kinematic pairs. So it is nothing but kinematic link. Two links, if I connect, we can call it as a pair, but the condition is these motion whatever with respect to one body, the other body should have relative motion. And we have discussed different types of relative motions, and according to the type of relative motion, according to the type of contact, and according to the type of closure. So first, according to the type of relative motions, we have discussed what turning pairs, spherical pair, screw pair, rolling pair, and spherical pair. These are the things. We have sliding pairs. We have discussed these things. And sliding pair is also called as prismatic pair. And according to the type of contact, we have discussed lower pair, higher pair, and wrapping pair. And the difference between lower pair and higher pair is lower pair, if at all it is a what, a surface contact. If at all it is a surface contact, we are going to call it as a lower pair. Higher pair is a point or line contact between two links. If the contact is of point or line, then we are going to call it as a higher pair. Wrapping pair, it is a combination of higher pairs, that means points. Example, I said wrapping of elastic material on a body, rigid body. Okay, so the last one is according to the type of closure. We have discussed this thing like uh, closed, like unclosed pair and closed pair we have discussed, and I've given examples of cam and follower. Okay, and also automatic door closures. These are the examples of different types of kinematic pairs. And next we went on to discuss about kinematic chain, and next, mechanism. So a kinematic chain can be called as a mechanism if one of the link is fixed. Next, we have discussed machine. It is a combination of mechanisms. For a given input, you are going to get output. Okay. Next, structure. A structure is nothing but a here the relative motion is 0. There will be no relative motion. It is a fixed body. So when there is no relative motion between body, we call it as a structure. So we have discussed these small definitions, and then we went on to discuss the important topic, that is degree of freedom. Degree of freedom, or it is also called as mobility of a mechanism. Okay, so it is mobility, or it is called as degree of freedom. So it is the minimum number of independent variables required to define the position or motion of a system or body. Okay, so this is degree of freedom. So again, I'm repeating, it is the minimum number of independent variables required to define the position or motion of a system. So this is degree of freedom. And then we went on to derive Grubler's equation, Kurzbach equation. Then we went on to discuss Grubler's equation and Kurzbach equation. Kurzbach equation. So in a plane, on a plane, like on a 2D diagram, so we have we have discussed the equation. So this is the body. How many degree of freedom is there according to, along x-axis and along y-axis, and with respect to the point or origin, this is the z-axis. So where if you have a point, so you have this rotation about z-axis. So in a space, in a like 2D plane, you have 3 degree of freedom. So two translations, and one rotation. So whereas in space, okay, where the third coordinate is also going to come in the picture, so you have 6 degree of freedom. So 3 rotations and 3 translations. That is about x, about y, about z translations. And about x, y, z, you have 3 rotations. We have discussed in detail all those things, and you will find out these things in my previous recordings. What is Kurzbach equation? Degree of freedom is equal to 3 into n minus 1 minus 2j minus h, 1 into h. So do you remember this equation? Ma? Hello?
Yes, sir.
Yes. What is 3 into n minus 1? These are number of
Lower.
possible degree of freedoms. Okay, for a body, in a mechanism. So n is nothing but what number of links. Okay, so how in each for each link, how many degree of freedom will be there in a planar motion? 3. So how many number of links are there? N number of links are there in a mechanism. So 3 into n is the possible number of degree of freedom you are going to get. But for a mechanism, one link is fixed. So one link degree of freedom is 0. So that's why this 3 into n minus 1 denotes number of possible motions you are going to get. So you are what subtracting these things, that is 2j and 1h. What is this 2j and 1h? See here, 2j is nothing but j is nothing but your lower pairs, and h is nothing but your higher pairs. So in this mechanism, suppose if this particular links are connected by using lower pairs, so how many restraints you are going to get? Two restraints are you are going to get. So example, you can take what a turning pair, or you can take a sliding pair. So we have discussed this degree of freedom. So you have only x, and about this thing you have rotation. So like in 2D space you have only, so here you have only x, in x direction you have motion. So in y direction you don't have, in z direction also you don't have. So here rotations are also restricted. Similarly, example, so here this is link 1 and link 2. So these two links were connected by using a turning pair. So if I fix this particular link 1, so link 2 is having only one option, that it can only swing or it can rotate with respect to link 1. So the remaining, what is the remaining? That is two translations, that is along x-axis and along y-axis. Here the motions are restricted. So if I connect by using any turning, any lower pace, so I'm going to get two restraints. So these are nothing but restraints. So here by if I connect by using lower pairs, I'm going to get two restraints. And if I connect by using a higher pair, I'm going to get only one restraint. Okay, so example, cam and follower. So you have this particular, this is nothing but follower, and this is nothing but cam. So this is link 1 and link 2. This is fixed link 3. And between these two links, you have a line contact. So here, what happens, there is no spring force, so it can easily reciprocate and it can easily slide. So that's why here you have only one restraint. That means it can not come in this direction. So because of this restriction, it can't move in right ways. Okay, so in higher pairs, you have only one restraint. These things we have discussed. So this formula is very, very important for gate perspective. So 3 into n minus 1 minus 2j minus 1h. So what is Grubler's equation now? So what Grubler did is he substituted. So he substituted f is equal to 1 and h is equal to 0. That means he didn't consider higher pairs in a mechanism, and he wants degree of freedom is 1. So he substituted these values in the Kurzbach equation and he derived one relation, and that is nothing but Grubler's equation. And these are the things we have discussed, and a few problems, very, very important problems we have discussed on degree of freedom. I hope you remember, and please practice those problems. Okay, and we have discussed then about simple mechanisms. That is the first simple mechanism we have discussed is 4-bar mechanism. So these are simple mechanisms. The first one is 4-bar mechanism we have discussed, and next is single slider crank mechanism. Single slider crank mechanism. And next we have discussed a double slider crank mechanism. So then we have discussed about inversion of a mechanism. I hope you remember about inversion. Do you remember about the inversion? When we are going to call it as inversion. Ma Raghunath and Vasudev.
If different links,
Yeah. So
if different links are fixed,
yeah. So here in 4-bar mechanism there are 4 links. So 4 bars or 4 links and 4 lower pairs, and all lower pairs are turning pairs. Okay, so if I fix one by one link, so total 4 links were there. So if I fix one by one link, so I'm going to get different mechanisms. So if the mechanisms are unique, then I'm going to call it as an inversion. Okay, so here in 4-bar mechanisms, how many inversions are there? Here I have 3 inversions. One is crank, so that means double crank mechanism. One is double crank. The other one is what? Crank rocker mechanism. And the third one is rocker mechanism. So double crank, that means when I'm going to call it as a crank, when a link is rotating 360 degrees, complete 360 degrees, then I'm going to call it as a crank. So double crank, that means input and output link both rotates 360 degrees. Next is crank rocker. That means one input link or output link, whatever may be the link. So if at all it is rotating 360 degrees, the other is oscillating. So rocker is nothing but oscillation. That means it is not going to complete 360 degrees. So whatever may be less than that angle, we're going to call it as a rocker. And next is rocker. That is input and output. Both the links are not going to rotate complete 360 degrees. Okay. So to obtain these mechanisms, so the law which is very important, that is Grashoff's law. So what Grashoff did, so it applies all the mechanisms, that is 4-bar, single slider, double slider. It is going to apply it in all the mechanism. So what he stated is sum of the shortest plus longest link should always be less than or equal to sum of the other 2 links, that is P and Q. Okay, in simple mechanisms, so all the pairs which we are going to use is lower pairs only. So how many links? 4 links we are going to use. Okay, and in those 4 links, the sum of the shortest plus longest link should always be less than or equal to sum of the other 2 links. That is the condition. If this condition is satisfied, you are going to get these mechanisms. If this condition is not going to satisfy, that is, if S plus L is greater than P plus Q, if this is going to happen, then whatever the link you are going to fix, you are going to obtain rocker mechanism. You are not going to get any crank. Okay, so if this is the law is not satisfied. These are the things we have discussed in my last class. And single slider crank mechanism. And in this single slider crank mechanism, how many inversions we have? Total 4 inversions we have. What are those 4 inversions we have discussed? One, if I fix, I'll draw here. So this is the single slider crank mechanism. This is my cylinder, and here is the piston. To the piston, connecting rod is connected, and to the connecting rod, crank is going to connect. Okay, and this is called as line of action. So this is single slider crank mechanism. So you have link 1, and we have discussed steam engine also. First pioneer, James Watt, he developed this particular steam engine. Thereafter, you got this particular petrol and diesel engine working with this. Okay, so here link 1, this is link 2, and link 3, and this is link 4. So fixed links are 1. Okay, so here how many links were there? 4 links, and all these 4 links. So between link 1 and link 2, link 4, you have a turning pair. So here this is one lower pair which is a turning pair, and this is another. So here I'm writing O, and this is A. So another lower pair is there here between 3 and 4, and between 3 and 2. So you have another a lower pair which is a turning pair. Okay, and between 1 and 2, so here you have a sliding pair, or we can also call it as a prismatic pair, and again it is a surface contact which is a lower pair. So here also all are lower pairs. So here in these 4 links, so first link I have fixed. So link 1 is fixed. So link 1 is what? Cylinder. So if I fix this particular cylinder, so here I'm just giving an input. So this is omega 4. So I'm just giving input to the crank. So crank which is rotating 360 degrees. So as crank is going to rotate, what is the final link or last link is the link number 2. So link number 2 is having only one motion, that is translation. So it only translates. That means here input is rotation, output is translation. So in next case, what I'm going to do, I'm going to give input towards link 2. So here I'm just giving the input. So what is input here now? Translation. The output I'm going to get is rotation. So this is nothing but where I'm going to use in reciprocating engines, like your petrol engine and diesel engine. And this is the case where you are going to get output as translation is compressors, reciprocating compressors, where you're going to fill your air for 2-wheelers, 4-wheelers, okay, whatever may be. So this is compressors. Sorry. So these are compressors. So when link 1 is fixed. Okay. So next is when link 4 is fixed. But I'll come to link 2 because here I've denoted different links. Okay, so link 2, which is a piston or a slider is fixed. So what is the mechanism we are going to get? Pendulum pump or hand pump. I hope you remember pendulum pump or hand pump. These are the things we are going to get. And when link 3 is fixed, so link 3, that is coupler, is fixed. What you're going to get, ma? So you're going to get two mechanisms. What are those mechanisms you are going to get? Quick return motion mechanism. Quick return motion mechanism. What is that? Crank and slotted lever. So we have discussed this in my last class. Crank and slotted lever, quick return motion mechanism. What is the second? What is the second you are going to get? Oscillating cylinder engine mechanism. So these are the things we are going to get if we fix coupler. And link 4, that is crank. When crank is fixed, what you're going to get? So again, two motions, we are going to get. The one is Whitworth quick return motion mechanism. Quick return motion mechanism. The next one is Gnome engine or rotary engine or rotary engine mechanism. So Raghunath and Vasutej, okay. So in these
Yes, sir.
mechanisms, which one we have discussed in the last class. So we have completed crank and slotted lever quick return motion mechanism, and we have also completed Whitworth quick return motion mechanism. So we need to complete oscillating cylinder, gnome, gnome engine, and pendulum pump or hand pump. So today we are going to discuss these things. Okay, so in between these two quick return motion mechanisms, which one we called it as best quick return motion mechanism? Gurtunda? So don't waste time. If you didn't remember, just tell me. I'll just recollect it.
No, sir.
సో ఫిగర్ డ్రాయింగ్ అన్ని చెప్పాను, అది కూడా గుర్తులేదా?
Figure gurtu.
Yeah. So in between these two, that quick return ratio we have discussed. What is quick return ratio? Beta by alpha. So here always quick return ratio is equal to or greater than or equal to 1. So this is about quick return ratio. And also we have discussed that is the stroke length. Stroke length. So here in so I'm just denoting this crank and slotted lever as 1 and Whitworth as 2. So in crank and slotted lever quick return motion mechanism, the stroke length is dependent on. So is dependent. We have derived it. So please go like take out your notes and see. Okay, it is dependent on how many factors? 3 factors. What is the first one? Crank length. It is dependent on crank length and connecting rod length. So, and it is also dependent on slotted lever length. Okay, so these are the 3 factors which are dependent. Okay, but what about in Whitworth quick return motion mechanism? In the second category, stroke length is going to dependent on only like maybe in the slotted bar. So I don't know. We have what letters we have denoted. So this is the extension link. So this point, suppose say C, and this point say M. So only on the distance between these two factors, that is CM, it is dependent. So in Whitworth quick return motion mechanism, only one factor comes into picture, but in crank and slotted lever quick return motion mechanism, so it is dependent on 3 factors, that is length of the slotted bar, length of the crank, and length of the connecting rod. So that is the only difference. So I hope you remember the figure also. If you have any doubts, you can please ask me. So till this point we have discussed in our last class. So shall I move to the new topic now?
Yes, sir. We can
Yes.
move.
Yeah.
Yes.
So next is we are going to discuss about oscillating cylinder engine mechanism. This is the third one. So it is also very, very important. So oscillating cylinder engine mechanism. So when I'm going to get this particular mechanism, which link is fixed here? Crank or connecting rod? So here connecting rod is fixed. See, please note in your bookmark. So if you are not noting down, so it will be a problem for you. Okay. So if connecting rod is fixed, so you are going to get a mechanism apart from quick return motion mechanism. You are also going to get oscillating cylinder engine mechanism. Okay. So you can see here a 3D picture I have shown you. So here this one is the cylinder. So this cylinder, say this is link 1, and sorry, 1 minute. So this one is cylinder. So I hope you can see it. This is cylinder. Okay, and internally you can see this one, and this one is piston or slider. Piston or slider, and this is piston rod, so there is no relative motion between this and this. So this one is crank, and here there is a fixed point, and here also a hinge point. So I'm just connecting these two. So because these two fixed, I can connect, and this one, whatever is there, it is coupler. So the distance is nothing but the coupler or connecting rod. Okay, so I'm just showing you as a 3D picture, but you can see here in detail it is there down. So you can see the connecting rod, that is link number 3, which we are going to fix, and this is link number 4, that which is cylinder. Cylinder is not fixed in this particular, and the crank and the piston rod. So as I already said, piston and piston rod. So you have piston and piston rod. So names were given both, but there is no relative motion. No relative motion between these two. Okay, these two were welded here together. So there will be no relative motion. So now, what happens if I give any input to the crank? Okay, so I have just given an input to the crank. So it starts rotating in anti-clockwise direction in this direction. So it impart some force on the piston rod. Okay, so what the piston rod is going to do, it imparts some force on the piston, and piston is going to, because it is having some relative motion with respect to the cylinder, that is the sliding motion, it is going to slide. So when it is going to slide, what happens, the link which is connected to the cylinder, so it is hinged at this particular point. You can see here it is hinged at these 2 points, this cylinder. So what happens, what is the relative motion, because it is a pin, so between this particular coupler and the cylinder you have a rotary motion, so it is going to swing here. So what happens, my cylinder is going to swing with respect to the connecting rod or coupler. Okay, so this is my output. In this manner we are going to call it as a oscillating cylinder engine mechanism. Okay, this is one such inversion. I hope you got it. So next is, so here my input, so you need to remember, so here your input is rotation, input is rotation, so output is here, because like translation, but here my cylinder is, so to get, in order to get translation, cylinder is going to oscillate. That is the difference. So in order to get translation, so my cylinder is oscillating. Okay, this is the third category. Next is the fourth one, which is rotary IC engine. So this is called as rotary engine, or a German scientist who pioneered this. Okay, so we call it as a Gnome engine also. So this is Gnome engine. So roughly how many cylinders you're going to get? 7 to 9 cylinders, or in some cases 7 to or 9 cylinders. Okay, here which link is fixed? Crank. Crank is the shortest link. This is the important point. Crank is fixed. And also here you need to remember one thing. So to all cylinders, so how many cylinders are there? Total 7 or 9 cylinders will be there. Okay, so for all cylinders you have only one, so I'll write here, one common crank. So as I said, like 7 cylinders, then sir, 7 cranks will be there, 7 couplers are going to be there, 7 sliders are going to be there. Yes, 7 sliders will be there, 7 couplers will be there, but you have only one crank to all the cylinders. Okay, so please do remember. Now what I'm going to do is, I'm just highlighting in the figure, so you can see the highlighted portion. So at one end is at the center, so I'm just naming it as the other end as O. and the other end, so I'm naming it as A, and to this A point, so this is what the crank, the orange color. So here one turning pair and here another turning pair will be there. So to this turning pair at the bottom, which I'm going to call it as O, and the other turning pair A. So at what point you have a bearing, so complete cylinder, whatever their housing is there, housing is connected at point O. Okay, bearings are there at point O, and at A, point A, so how many number of cylinders are there? Total 7 cylinders are there here. So here I'm just naming 1, 2, 3, 4, 5, 6, 7. So here in this 7 cylinders were there. So to these 7 cylinders, 7 couplers are going to be there. So all the couplers are connected at point A. So whatever may be. So these are the things are connected. So by using a turning pair itself. So here you can see here another turning pair will be there. Okay, okay. So you can see the positions of the slider in each cylinder. So we need to place these positions in such a way that, so we need to make sure that at a time you won't get combustion in each and every cylinder. So for a period of time, so say 2 seconds in one cylinder, if you are receiving power, the other cylinder after 2 seconds you need to get. Okay, after 2 seconds in another cylinder. So that's why these positions were timed or placed in this manner. Okay, so you can see the positions of the coupler too. So in cylinder 1, see the gap between the gap of the combustion chamber or inside cylinder. You can see here the position of the piston, moreover it's like top dead center, in the top dead center. In second cylinder it is somewhat uh, coming towards the crank, and in the third also somewhat the gap is more in fourth, fifth, and also sorry, here you can see in sixth and seventh, and this is link 3 piston and link 1 is cylinder. So what happens here, if you observe carefully, now in cylinder 1, what happened, this piston position is at top dead center. Okay, so that means here it is, I'm going to suck my fuel, it is in the starting stage. Now, so similarly the second, third, fourth, but here if you observe in the fifth cylinder, when compared to the fourth cylinder, it is trying to move towards the top dead center, from the bottom dead center to the top dead center. That means the compression is going to takes place. Okay, so if you see in the sixth and seventh cylinder, the compression is going on happen. Okay, what happens at a time interval? So in a cycle, so combustion is going to takes place. So when the combustion is going to takes place, what happens? The slider example, if you take this second slider, suppose here I got combustion, so I'm just representing it here. So I got here combustion. So due to this combustion or heat energy, so there is a force which is applied on the slider. Okay, so slider, so what happens, slider tries to move downwards, inwards, so it is applying some force on the coupler. So when the force applied on the coupler, what happens, so but the other end, which is crank is fixed, right? So here the crank got fixed. So here I'm just drawing here. So here the crank got fixed. So when the crank is fixed, so obviously crank is not going to move. So what happens here, my coupler, so it has to transmit some force, but the other end, which is connected here, the slider, so it has only one option, that is my slider is going to slide as well as 1 minute. So it is going to slide as well as it tries to apply some force on the cylinder. Okay, and cylinder with respect to point O, Okay, the housings are there, complete bearings, so it has free to move in, free to rotate. So what happens is, cylinder is going to move. So similarly, the respective cylinders, whatever there, third, fourth. So if the combustion is going to take place inside the cylinder, so input force comes on the piston. So please do remember these points. So I'm going to write here. So I'll write here. Yeah. So first point, combustion combustion takes place inside the inside the cylinder. What happens if combustion takes place? Input force, that is whatever the heat energy is there, comes or exerts on to the piston. This is the second point. So what happens if the piston is going to receive? So this force, whatever the force is there, so force is going to get transmitted to what? The link connected to the piston. What is the link? That is connecting rod. So it transmits to connecting rod. Then what connecting rod is going to do? So connecting rod rotates because it is not going to uh, what transmit. The other link is fixed. What is the other link? The crank. So
Crank.
connecting rod rotates about point A. Pardon ma?
Nothing, sir. I'm saying that crank is fixed.
Yeah, yeah. So connecting rod rotates about here because crank is fixed. So connecting rod and crank were connected by using a turning pair. So you have one motion, that is rotation. So here my connecting rod rotates about point A. So what happens if it is going to rotate? So again my piston, because when the connecting rod starts rotating, so piston is also connected to the connecting rod at the other end. So piston also going to rotate. Piston rotates. So when the piston is rotating, what happens? Piston is connected to the cylinder block. So cylinder, sorry, cylinder block rotates about point O. So cylinder block rotates about point O. So this is nothing but your output. Okay. So this type of engines is used in aircraft for what? To get high propulsion. In aircrafts, to get high propulsion. So used in aircrafts to get high propulsion. So I hope you remember in aeroplanes the engines were placed while it is moving. You can see from the front. Okay, so these are rotary engines. So this is the story about the what a rotary engine where crank is fixed. So next we move on to the next topic, which is hand pump. I hope in villages also you have seen this particular hand pump. Yes or no?
Yes, sir.
Yeah. So I'm just showing you a hand pump. So I'll just draw in this board. So we'll correlate with the figure which is there towards your left. Okay. So please do remember what I am just drawing. So here what I'm going to do is I'll just draw this particular mechanism. Uh, I'm just rotating it to 90 degrees. So you can see this is my line of action. So here is my slider. I'm just drawing somewhat bigger. Okay. And to this, I have a cylinder. So to understand purpose only, I'm just drawing it. Otherwise, you may get confused. So this is my cylinder earlier. This is my what slider. So to the slider, the link which is going to connect is coupler. So this is my coupler, and this is my crank. This crank is going to rotate about this particular point. So here the last inversion, that is when the slider is fixed. So what I'm going to do, observe carefully what I'm going to do. So I'm just taking eraser, I'm just erasing this particular part. Okay, I'm considering only slider. I'm considering only slider. So basically the slider, what is the cross section here? Circular. It is a circular cross section. So what I'm going to do is I'm going to drill it. I hope you know the function of drilling. Drilling is nothing but making a hole. Okay, so if I'm looking from the top, so if I'm looking here, so the cross section is like this. So everything, because it is a piston, so it is solid. So what I'm going to do is I'm just going to drill it. Just drill it like this.
Hollow cylinders.
Yeah. Similarly like that, but not to the bottom, only up to this much. So it's like counter bore operation. Similarly, at the bottom also I'm going to do the same thing. I hope you got it right.
Yes, sir.
Yeah. So it's like some part of the material is removed from the top, and also from the bottom it I've removed it. Okay. Now I'll ask you one question. Please tell me. So here towards your left you can see the hand pump. Now how this particular hand pump is going to work, how the water from the ground is going to fill in the bucket, how it is going to come, do you know that?
No, sir. Don't know.
So you are going to what, you're going to use your hand, and you're going to pull this particular handle, you're going to swing this particular handle up and down, yes or no?
Yes, sir.
So what happens, so you are like what there is a pressure difference here at the inside the body in this particular link. So you are creating vacuum. So by swinging like this, so you are creating a pressure difference. So to this particular link, you can see a link here which is connected by using a turning pair, and here also you can see this is nothing but the piston rod, and to this piston is or we can say the second slider is going to connect it. So I'm just drawing it large, this particular link. So I'm naming it as link number say 1. So I'm just drawing here this 1. So another slider is there like this. You can say like కవ్వం అని తెలుగులో అంటారు, లైక్ పప్పు గుత్తి ఏదైనా తీసుకోండి, లైక్ దట్ ఎగ్జాంపుల్. సో వాట్ ఐఎమ్ గోయింగ్ టు డూ ఈస్ ఐఎమ్ గోయింగ్ టు do it, I'm going to suck it like this. So do you know the function of suction, right? తెలుసా
Yes,
అమ్మ?
sir. Yes, sir.
పైప్ వాటర్ లో పెట్టి if you suck it, the water is
పీల్చుకుంటుంది.
going to get left. So why the water is coming upwards or inside your mouth is due to the pressure difference. You are creating vacuum inside it. So how you are going to create a vacuum? So this is the way to create pressure difference. So what I'm going to do is to create pressure difference. So I'm going to take a smaller drill now, and I'm going to drill it here like this. So two small holes. So in the front view you can see like this. So in the top view you can see a small holes in this manner. I hope you got it right.
Yes, sir. Got it.
Yeah, these small holes. So I've drilled a small holes. Now what I'm going to do is I'm going to take another link. So now I'm going to place it here. And to this particular link, so I'm going to, this is one link, there is no relative motion between these two different. Okay, so now what I'm going to do is, so this link I have placed, and this link, so say this is 1, 2, oh sorry, it's not fixed, it is a turning pair. So this is my link 2 and 3. So here is my slider 4, and here my, in place of cylinder I'm keeping a secondary slider in it. Okay, so what happens, so because here my this particular body, fourth number link number 4 got fixed, so this link number 3 is hinged to link number 4. So this particular turning pair cannot move. So what I'm going to do is I'm going to add this crank. The second link is there, right? So this is my second link. So this is the second link. So I'm just extending this second link. Okay, I have extended this second link. So after extension, now you are handling this particular link. So with respect to this particular turning pair, which is there, TP, which is there, so I'm going to pull it downwards. So when I'm pulling it downwards, what happens, here you have a turning pair, and here also you have a turning pair. So this particular link number 1 is restricted to move only in up and down direction. Okay, so what happens if you are moving downwards, so it is going to link number 1. So link number 1, so it starts moving upwards. So say this is point number O, so it has moved to O dash. So when this particular point is moving downwards, so now I'm going to shift this particular link like this. I hope you got it. So here my slider is moving somewhat upwards. These are the dotted lines. So this is the first position, that is, I'll say O, and this point is A, and this point is B. B is the fixed point. So O, A, B is my first position, and O dash, A dash, and this particular, sorry, on the slider, right? So I'm keeping this particular B point on this particular point B. So here next is B dash. So O dash, A dash, B dash is the new position. So what happens when the slider is moving up and down? Okay, so up and down. So you are creating this particular what suction inside this particular body. So here you are creating suction or pressure difference. So due to this pressure difference, what happens? The water is going to flow upward direction. So here the water is going to come. So in this manner, this hand pump is going to work. So due to the movement of the plunger, or you may take the second slider, so pressure difference is created and the water flows towards up. So this is the story about different types of mechanisms in single slider crank mechanism, different types of inversions. Now we'll discuss the third category. So what is the third category? Double slider crank chain. So third simple mechanism is double slider crank chain or mechanism. So here I'm calling it as chain. Why I'm not going to call it as mechanism is I'm not going to fix any of the link. That's why I'm calling it as chain. So I'll just draw it. So meanwhile you also can draw. So Is there any doubts up till now?
No doubt, sir. Okay.
Okay. Okay. Hello?
Sir, Chapan.
Yeah, yeah. So I'm just drawing, so I took a while. So this is link one, ma. So link one. Everything. This is a slotted plate. You can say a slotted plate. Just drawing the top view of it. So it's a slotted plate and I'm naming it as link one. Okay, now I'm taking link number two, which is a slider. Okay, and I'm placing another slider here. So, so here the name indicates double slider crank chain. So double slider means nothing but we are using two sliders. Okay, and crank is nothing but one which is rotating. So here I'm just connecting a link which is connected to these two sliders. Okay, so here the link which is connected to both the slider, I'm naming it as link number 2, and the slider is link number 3, and another slider is link number 4. Okay, so in the slotted plate, what happened? I'm just arranging these two sliders in the slotted plate, one in the X direction, the other in the Y direction. Okay, so this is the 2D representation. So in the 3D, you can see here. So can you see it? So this is the slotted plate. Ma, can you see it?
Oh, yes, sir.
Yeah. So you can see this is the slotted plate, only one link. Okay, so this is link 1, and the link, so here you can see this is link number 2, and here you can see a slotted, so you can see here a slotted, sorry, a slider, which is link number 3, and this is, there is another slider here which you can't see, so this is 4. So between the slots, so in the slots, these sliders are going to get are going to reciprocate or translate. Okay, so this is a link which is connected to two sliders by using a turning pair. Okay, so here what I'm going to do is, total 4 links are there. So 2 sliding pairs and 2 turning pairs. So 2 sliding pairs or prismatic pairs and 2 turning pairs. Both are lower pairs only. Okay, so what happens? I need to fix. So double slider crank chain it is. So what I'm going to do is, I'm going to take first inversion. So I'm fixing one link. So now, so what I'm going to do is, I'm going to fix this particular slotted plate. So first I'm fixing link 1, which is a slotted, link 1 is fixed, which is a slotted plate.
Sir, initially no link is fixed, sir.
See, when I'm going to call it as a chain,
Yes, sir.
chain means that is nothing but a mechanism, not a mechanism. Yes or no? So when chain can be called as a mechanism, when I'm going to fix a link, right?
Yes,
so first I'm fixing a link. So which link we are going to fix first? Link number 1 I'm going to fix.
Slotted plate.
Yeah. So if I'm fixing that particular link, what I'm going to get is, I'm going to get a mechanism which is called as elliptical trammel. So this is the application. So elliptical trammel you are going to get. Shall I use the same figure or see? You can see the device, right? Can you see the device here?
Yes, sir. You can.
So this is the link. Here at this particular position, we are going to place a pencil or pen on the sheet at this particular position. So what you're going to do is, you're going to reciprocate this particular link. You are going to give an input here. So if you're going input, or you can connect a motor on this turning pair. So when it starts rotating, what happens? So here, because it is fixed, right? So my slotted plate will not move. So what happens? My like a slider which is there, it is going to rotate like this. Sorry, translate like this. So when it is coming towards here, this particular link which is connected to this slider, so it pushes this particular slider in this particular positive y direction. So when it is moving in negative x direction, it moves in positive y direction. The second slider will move in positive y direction. So here, whatever the point you are going to trace, so this locus of all the points, if you start tracing it, you are going to get ellipse. I hope you know what is ellipse. Tells kada?
Yes, sir. Tells.
Okay, so you're going to get ellipse. So in this way, you will get major axis and minor axis. So how you are going to get major axis and how you are going to get minor axis, we are going to discuss now. Okay, I hope you have understood, right? So here I'm fixing this particular slotted plate. So if I fix this slotted plate, I'm just giving an input to the one of the slider, or you can what extension link, whatever maybe. If you move or apply force, this particular what link number 3, which is a slider, it starts moving in a minus x direction, negative x direction, and the other slide, because the link which is connected to this particular slider 3, okay, so it applies some force in this positive y direction and it starts moving in positive y direction. So it is going to come here in negative y and positive. Then afterwards, it further moves in this direction. Then what happens? This particular slider is going to move in negative y direction. It comes at the center point. Okay. Then if you pull it back in negative y direction further, it starts moving in positive x direction. That is link number 3. So in this manner, you are going to trace this particular ellipse. Okay, and we'll discuss this particular how you are going to get. Sir, how can you judge that whatever the point you are going to trace, all those locus points you are going to trace, it forms ellipse? How can you judge? So here we are going to derive this equation. So I'm going to show you now. So we'll see. I'm just drawing this particular graph. So I'm just plotting x-axis. This is my x-axis. I'll plot a y-axis. One minute. So this is my y-axis. So this is x and this is y and this is point origin. So I'm just drawn the same orientation of this particular slotted bar now. So this is my x-axis, y-axis, and I took this as x-axis, and I've plotted here. And this particular white color line, sorry, and this particular white color line, it is the representation of this particular link which is connected to both the sliders. And here is the position of one slider, and here is the position of the other slider. So we'll leave it. So I have drawn this, and the position of the link number 3, that is slider, I'm naming it as point B. And here the other slider, that is which is fourth link, I have named it as A. Okay, so you can take any of the point on this line, the link which is connected to third and fourth. You can take any point. You can. How many points are there on this particular link? Can anybody tell me?
Infinite number of points.
Yeah, infinite number of points. On these infinite number of points, you can take any of the points. So here I am taking as such as here this point as P, and this P point I am taking it as x comma y. So x-axis you have 1, and in y-axis, so I'm just drawing it. So this is x, and similarly y. So I'm defining this particular point with respect to x and y, and this distance is nothing but x distance, and this distance is nothing but the y distance. So you can take triangles. So if you observe here carefully, A, P, and this particular triangle, this particular say O1, and here you can take O2. This point as O2. And if you observe this particular triangle A, P, O1, and similarly P, B, O2, the angle here and the angle here, both are same or different? Both
Same,
are
sir.
same. Those are nothing but similar triangles. Okay, so you can take this small triangle. So you can take small triangle. So what is the triangle? A, P, O1. So what I can do is I can take as cos theta. What is cos theta? Opposite by adjacent, right?
Adjacent by hypotenuse.
Adjacent by hypotenuse. Yes. What is the adjacent?
X, sir.
X. What is the hypotenuse value?
AP.
AP. Very good. Similarly, you can take a triangle P, P, O2. From this triangle, you can take sine theta is equal to, can you tell me opposite by hypotenuse, right? What is opposite? Y.
Y by PB.
BP or PB.
B. Yes, sir.
Okay, so okay, say this as equation 1 and say this as equation number 2. What you're going to do is you just square and add these two equations. Squaring and add, so squaring and adding equations 1 and 2. What you're going to get, ma? So cos squared theta plus sin squared theta, what is that value?
1, sir.
1. Very good. So 1 is equal to, next I can write x square by AP whole square plus y square divided by BP square. Okay, now just tell me what is this equation called as?
Ellipse equation.
Ellipse equation. I hope you remember. So now, so you can take any of the point. You can take any of the point on this particular line. Okay, so the angles will be same for the both the triangles. So you can trace what is the what figure, what shape you can trace. You can trace ellipse. Okay,
Ellipse.
and I can say AP as semi major axis and BP as semi minor axis. So I hope you know ellipse, right? So you can see here, and just I'll just plot it. So this is y axis, and this is x axis. So this shape is ellipse, and you can take, this is AP semi major axis, and this is BP, which is semi minor axis. Okay, and similarly the ellipse orientation may be like this also. So here AP becomes minor and BP becomes major. Based on the questions, you need to plot the figure. Okay, so what is the first inversion? We have discussed elliptical triangle. So this is very, very important. You may get, sorry, you may get questions, gate questions on this topic too. So this is the first inversion. The second inversion. So what we have to discuss, second inversion. You can fix now. What are the options you have, ma? You can fix slider,
Crank.
or you can fix the link which is connected to both the sliders. So first what we are going to do is we are going to fix a slider. That means the link number 3 or link number 4. Now if you observe here, if I fix this particular link number 3 or 4, you are going to get the same mechanism, yes or no?
Yes, sir.
Yes, yeah. So observe here carefully. Now, so in the 3D picture, if you can see the third link, so if you can see the third link. So if I fix the third link, what happens? What happens if I fix the third link? The other fourth link is there. So you are going to apply a motor on this particular turning pair. So suppose link 3 is fixed or link 4 is fixed. So I'm fixing here link 3. Basically, yeah. So link 3 is fixed. So you're going to get Scotch-Yoke mechanism. I'll tell you why this particular Scotch-Yoke came into picture. Where is link 3? Sorry, it's easy for us to fix this second slider, ma. Link 3 or link 4 is fixed. So I'm fixing this particular link 4. Okay. Now just tell me if I fix this particular link 4. what happens? And what I'm going to do is I'm going to use this particular motor. So there is a turning pair here, right? So I'm going to use a motor. So to this particular motor, so I'm going to use this motor for this pair. Which link is connected to this? So the link which is connected to uh, both the sliders is given an input. So what happens due to the rotation, this particular link, that is the second link, is going to rotate. Yes or no, ma?
Yes, sir.
Yes. When it starts rotating, so it imparts some force on link number 3, that is other slider. So what happens, this particular slider is going to push or apply force on the what slotted plate. Yes or no? Similarly, like in our rotary engine, so here also, so when it applies some force on the slotted plate, so here the slotted plate, what it is going to do, it has to move in this particular direction. Yes or no? But there is a restriction that the slotted plate can only move in positive and negative x direction. Why? Because you can see here the fourth link is fixed, so fourth link is not going to move. Only slotted plate is having only one motion, that with respect to this particular fourth link, it can move only in this particular positive x and negative x direction. So what happens when the third link is going to apply some force and the second link starts rotating, this slotted plate is going to move in negative x direction. Okay, or else when I'm going to give in clockwise rotation, that is input, if I'm going to give in clockwise direction, so my this particular third link is going, the direction is in this manner. So what happens, it will move, the slotted plate will move in positive x direction. Okay, so that means here my input is rotation. So here in this, input is rotation, the output is what?
Reciprocate.
Reciprocation or translation.
Oh.
Okay, so in this manner I'm going to use. So one such mechanism where I'm going to apply this is Scotch-Yoke mechanism. So this is Scotch-Yoke mechanism. I don't know how many of you observed in your manufacturing laboratory or machine tools laboratory. So cutting machines are there. మీకు వెల్డింగ్ బ్లాంక్స్ కానీ గ్రైండింగ్ పీసెస్ కానీ మీ వర్క్షాప్లో కట్ చేస్తారు, పెద్ద పెద్ద పట్టీల దగ్గర నుంచి చిన్న చిన్న ముక్కల్లా కట్ చేస్తారు అనమాట. It's like a power hacksaw. I don't know how many of you seen this power hacksaw. This is nothing but Scotch-Yoke mechanism. So if you observe here, this is link number, say what I can say, this is slot, I'm going to say slotted plate. So here I'm fixing what slider, right? So this is my slider, you can take whatever maybe. So here I'm link 1 and this is link 2 and this is link 3 and this is link 4. Okay, so here if you observe one thing, that is sorry ma, 1 2 3, yeah, okay. So what I'm going to do is I'm going to give input motion to the crank. So when this crank starts rotating, what happens, it imparts some, sorry, this I forgot, 1 minute, I did a mistake. Yeah, so if you observe here, this is link 1, which is a slider, and the black color one, here you can see the black color, this is another slider. So here I am naming it as a fourth. So here 1 and 4 are sliders, otherwise it's better to write this is third link and fourth link and this is link number 1, because my slotted plate has having only it can only move in positive and negative x direction. So this is negative x and positive x. So I'm fixing this particular third link. So third and fourth both are sliders, so I'm fixing those third link. So to the third link, by using a turning pair, crank is connected, and to the other end of the crank another slider is there, that is the fourth link. So slider is connected. So what happens when this second link is going to rotate? It obviously imparts some force on this particular slider. So it tries to move in this particular direction. So this slider is sliding with respect to the slotted plate. So it imparts force on the slotted plate. Now this slotted plate with respect to the link number 3, okay, with respect to the link number 3, it can only have one motion, that is translation. So as it is rotating, so when the crank starts rotating in 360 degrees, so it is going to move in positive and negative x direction. So basically in place of this link number 1, we are going to keep hacksaw. So it is called as power hacksaw, and here there will be some setup in our laboratory. Okay, so where some plates are mounted here. So in this manner, when it is moving to and from motion, so your cutting action is going to take place. So this is the Scotch yoke mechanism. That is when I'm fixing any of the slider, that is third link and fourth link. Now comes the last category, that is when link number 2 is fixed. So this is very, very important. So in machine drawing also you people have studied. So when link 2 is fixed. So by looking at the figure, I hope, can you remember? Have you studied this?
Yes, sir. We studied.
What is this?
No.
This is Oldham coupling. Oldham's coupling. So here what we are going to do is, so the link connected to two sliders. So where is the, yeah. So here what I'm going to do is I'm going to fix this particular link 2. So what happens if link 2 is fixed? So you, what is the condition here? The input and output needs to be connected to the fixed link. That is the beauty of the fixing. So here input is again a slider. The output is also again a slider. So here with respect to the link 4, link 2 is connected by using a turning pair. And with respect to link 3 and link 2, both are connected by using again a turning pair. So what is nothing but your input and output both, what you're going to get here? Can anybody tell me?
Sir?
Have you understood what I asked? Yes, hello Raghunath. Have you understood? See, basically this is link number 2. Yes or no? So link 2 is connected to a slider 3 and to slider 4 by using what, ma? By using a turning pair.
No.
Yes or no?
Yes,
By
sir.
using a turning pair. Now just tell me, so here you are going to give suppose input and here you are going to get output. Yes or no if I'm fixing? That is the beauty of the fixing, as I said in my last classes. So fixed link is called as a best position. Why? Input and output you can you are going to get by using within the fixed link. So one end I'm going to give input. So suppose if I'm connecting a motor at this particular point at 4. Now just tell me one thing, at this particular point I have to connect. So by using a turning pair. Now what this slider is having, slider is going to do, slider starts rotating, right?
Yes, sir. It will start turning.
Yeah, it starts rotating. So when it is going to rotate, obviously this particular slider is connected inside a slotted plate. Now when it starts imparting, what happens? This slider when it is rotating, because now just tell me one thing, how many relative motions will be there for a rectangular hole and a rectangular shaft? Any relative motions untayamma?
Only one, sir.
Only one. Yes, so very good. So here it can only slide. Yes or no? It is. This is the only relative motion. But here my input is nothing but rotation. So what? There is no translation here. So obviously my slotted plate, which is connected by using a sliding pair to the slider, what it has to do? It has only one option. Em chestadi adi kuda? What it is going to do?
Rotate, sir.
Yes, it starts rotating. So when it is going to rotate, it is also going to rotate. So when the slotted plate is going to rotate, obviously the link, that is the fourth link which is connected to the slotted plate, also going to rotate,
Rotate.
because there is a turning pair only. Yes or no? So it
Yes,
also
sir.
starts rotating. So here my output is also going to rotate. So here my input and output both are rotations itself.
Rotations.
So now where I'm going to apply this? So I'm going to apply. So now here, if you observe carefully, Nana, now just tell me one thing. So here I've kept a shaft in this turning pair. I've kept a shaft, and here also I've kept a shaft. Now just tell me, both the axes of the shafts are same or different? ఆ రెండు axes same or different? రెండు shafts కిను.
Axis different, sir.
Yes, very good. Axes are different. So
Yes, sir.
if I take this as my y-axis, and if I take this as my x-axis, so with respect to x-axis, or this is the origin, so with respect to the origin, the second or third shaft axis is placed at x distance, yes or no? And this fourth shaft is placed at y distance. So here x distance is 0 and y distance here is 0. So that means here I'm going to get the same output. Okay, if I'm giving input as say 200 rpm, I'm going to receive output also same 200 rpm. Okay, but the axis of both the shafts are different. X distance is 0 in fourth shaft, and y distance is 0 with respect to the third shaft. So here the condition is, so whatever may be the shaft's orientation, so you are going to get input and output as same. So that example is nothing but your Oldham coupling. Okay, so here you have how many links? So say this is 1 minute. What happened? Yeah. So this is link number 1 example, and this is link number 2, and the black color one is link number 3, and here shafts and all those things were not given, but shafts need to be given. The link, suppose here I'm just drawing it by using white color one. Yeah, so here the shaft will be there. These shafts were guided. So here also shafts will be there. Okay. And now understand one thing. Observe this particular third link. Okay. So this particular third link, the beauty of the third link is such that it is having 2 slots. So I'm just drawing its front view. So it is having 2 slots, one slot in this direction along y. So I'll just show you. So there is a slot here. I don't know why, because it is black. You can see here also a slot. Okay, and here in this particular direction, there is along x-axis a slot is there. So in the front view, you can see here slot. There is a slot here along y-axis, and along x-axis, the other side you have a slot. So what you're going to do is you're going to match with respect to link 1 to link 3, you are going to connect along x-axis. So here you have a connection. So after connecting these two, so that means these two components will have relative motion along x-axis. Okay, along y-axis, the relative motions were, along y-axis, the relative motion is restricted if you connect 1 and 3. Have you got it, ma? So please say yes if you got it.
Yes, sir.
Yes. Okay. So now concentrate on link 3 and link 2. So if I connect link 2 to link 3, so along y-axis, you have a relative motion. It can slide along y-axis. Okay, but along x-axis, here it got restricted. Similarly, with respect to 1 and 3, how a y-axis is restricted, and between 3 and 2, Here x-axis got restricted. So here if the shaft, suppose if this particular shaft is there some above along the origin, suppose it is placed at a distance of say 20 mm or 30 mm. Okay, so I can slide with respect to the third link, the second link somewhat upwards and connect to the shaft. So with respect to the other shaft, this shaft is placed laterally to some extent, to some distance 20 mm. But the input and output, that is the input rotation and the output rotation, is not going to get affected. Got it? Have you got it, ma?
Yes, sir. Got it.
Yeah. So this is the this is the story of simple mechanisms, and we have concluded the first part in theory of machines, or the first unit we can say in theory of machines. Okay, and we'll discuss some gate questions. So afterwards we'll move on to the velocity diagrams. So do you have any doubts
No, sir.
in the first part? I think it's clear, right?
Yes, sir.
So we'll discuss some gate questions and we'll move on to the next topic. Okay, so if you see here, we are discussing in the last class about degrees of freedom. Up to the third question we have discussed, and we'll discuss now the fifth. Seema, you have to take your book and pen, calculators with you, and please let me know the answers. Okay, so fifth question. What is the answer to the fifth question? So the number of degrees of freedom of a 5-link planar mechanism with 5 revolute pairs as shown in the figure. So you can see here, so this is the mechanism. So how many links are there? Total 5 links were there, and these 5 links were marked. And this is the first turning pair 1, and this is 2, again turning pair 3, 4 and 5. So how many turning pairs are there? Total 5 turning pairs are there, and all the turning pairs are what? Comes under which category? Lower pair or higher pair?
Lower pair, sir.
Yes, lower pairs. So how many number of links are there? N is equal to 5.
5.
Number of lower pairs, that is J, is equal to also 5.
5.
Now is there any higher pair here?
No, sir.
No higher pair, that is equal to 0. So what is the formula? F is equal to 3 into
S.
n minus 1 minus 2j minus
2j.
h.
Minus H.
Okay, so which is equal to 3 into 5 minus 1 minus 2 into j is 5. So 3 4s are what? 12.
12
minus 2 5s
10.
are 10, which is equal to?
2, sir.
That's it, 2. So here the answer is what?
C.
Answer is C.
Option.
Option C. So these are the questions you are going to get for 2 marks. Nowadays they are giving for I think 1 mark, but hardly you are going to get 2 marks. And match the following, here also 2 marks. This question in gate 2 2004, 2 marks. See how important these things. It's very easy. So he's asking you, so type of joint, degrees of constraint he is asking. What is meant by a constraint? Constraint ante ఏంటమ్మా? Hello?
Sir.
What is the meaning of constraint? చెప్పాను constraint అంటే ఏంటో కూడా. Constraint is nothing but restriction.
Restriction.
సో ఒక్కొక్క రివల్యూట్ జాయింట్ లో ఎన్ని రెస్ట్రిక్షన్స్ ఉన్నాయని అడుగుతున్నాడు అనమాట వాడు. అర్థమైందా? సో ఇన్ రివల్యూట్ పేర్, ఫస్ట్ వాట్ ఈస్ ద రివల్యూట్ పేర్? సో దిస్ ఇస్ లింక్ 1 అండ్ లింక్ 2. సో దిస్ ఇస్ నథింగ్ బట్ రివల్యూట్ అన్న టర్నింగ్ పేర్ అన్న ఒకటే. సో దిస్ ఇస్ టర్నింగ్ పేర్. సో ఇఫ్ ఐఎమ్ ఫిక్సింగ్ దిస్ పర్టికులర్ లింక్ 1, so how many motions this link 2 can get?
Only one revolution pair.
Only one, that is rotation you are going to get. So x along x axis and along y axis both are restricted, yes or no?
Yes, sir.
So how many restraints or constraints are there?
2, sir.
2. Very good. So I hope you got it now. Clear, yes or no?
Yes, sir. Yes.
So the P goes to 4. Okay, now what about Q? Cylindrical pair, how many are there. Cylindrical, if I say, it comes under 6 degrees of motion, that is 3D. Cylindrical ante 3D picture loki veltundi. So now just tell me, how many restraints are there for cylindrical? Any constraints unnai? Hello?
Sir.
How many? Is there any restraints for cylindrical pair? So you have here, suppose this is a cylinder, okay, and oh sorry. So with respect to this particular link 1, so link 2 is having 1 translation, and along the x-axis, along the axis you have rotation. Yes or no? How many degree of freedom you have? 1 along x-axis. Yes or no?
Yes, sir.
1 about this point you have a rotation.
Rotation.
So how many restraints now you have?
4, sir.
4 restraints. Okay. So next it goes to cylindrical, Q goes to 3.
3.
Okay, next spherical. In the spherical pair, as I said, like this thing, pen and the ball and socket joint, or you can see your neck. Along x-axis you can rotate, along y-axis you can rotate, along z-axis also you can rotate. Yes or no?
0 constraints.
0
Constraints.
0 constraints or 3. Do you have x-axis rotation in the spherical joint? Take an example of your head itself. Got it? Take an example of your head itself. So you can rotate about x-axis, you can rotate about y-axis, and you can rotate about z-axis. Can you move along y-axis? Translation motion untunda nee head ki?
Yeah.
Do you have? Do
No,
you
sir,
have?
no.
No, right? Along y-axis? Translatory motion along y-axis?
No, sir.
No, along z-axis?
Translation. No,
No, right?
translation.
So translation motions won't be there in spherical joints. Okay.
Yes.
So how many restrictions you have now?
3 restrictions.
So 3 restrictions. So it goes to 1. So the answer, the answer is now P is 4 and Q is 3 and R is 1. Is there any option? 4, 3, 1. You don't have any option.
No.
So I think like there might be some mistakes. So spherical pair. Okay, well, constraint is nothing but restrictions only. So you have 4 restrictions. The daddy didn't stick. 1 minute, ma. Give me a minute. Oh, I think like 1 minute. See, here we consider. Sorry, ma. One thing I'll do. Here he given about 6 degree of freedom example. Yes or no? So we made a mistake. First example we took as 2D. So if you observe here, 1 minute. If you observe here in revolute pair, so revolute pair is nothing but in 6 degree of freedom. So you have only 1 degree of freedom, right? So this is revolute. With respect to 1 and 2, you have only one motion, that is translation. Yes or no? Only in this direction you have rotation. Sorry, there is no translation. So about z-axis also you don't have. About y-axis also you don't have rotation. Okay, and so along x-axis you can't have translation. Along y-axis and also along z-axis you don't have. So these were not possible. So how many restrictions in 3D? You have 5 restrictions.
Restriction.
5 restrictions. So that means P goes to 2.
Option C.
That's it, right?
Yes, sir.
So P goes
Option
to 5. A option number 2,
C.
right?
C.
No, P option number is like you have 5 restrictions. 5 restrictions is nothing but 2, right?
Option 2. See, option C, sir. P2, Q3, R1.
Q3 and R
R1.
1. Okay. So we did Q and R, but P we have considered in 2D. Sorry. So
Yes,
what
sir.
is the option?
C.
Option number is C.
C, sir.
Okay. Good. So we have completed. So we back 2 marks here. So I don't know whether your confidence is gaining or not. So if you do these gate questions, it's more than enough. So I hope you are getting, yes or no?
Yes, sir. Getting.
Yeah. So next in the 7th question, a planar mechanism has 8 links and 10 rotary joints. What is nothing but rotary? Rotary is nothing but revolute pairs only, right?
Yes, sir.
So all are lower pairs. So here n is equal to how many number of links? 8.
8.
So j is equal to 10. So the number of degrees of freedom of the mechanism. So he is asking f value. So
1.
directly you can substitute.
Yes,
So
sir.
3 into 8 minus 1 minus 2 into 10. So minus
21 minus
is equal to 0. So 3 sevens are how much? 21 minus 20. So how much?
1.
1. So
Option
what is
B.
the option?
B, sir.
Option B. So option B. So here also they are going to give for 1 or 2 marks, so I didn't remember. Marks were not given. Okay. So next, the question given in GATE 2010. So read the question properly. Read the questions properly in this category. So he's asking you to like find incorrect statement in the following. Okay. So which of the following statement is incorrect? So Grashoff's rule states that for a planar crank rocker 4-bar mechanism, the sum of the shortest and longest link lengths cannot be less than the sum of the remaining 2 link lengths. So here that is S plus L. What is Grashoff's law? What is Grashoff's law?
Less than or equal to sum of other two.
Sum of other two. This is what Grashoff's law. So
Yes,
he
sir.
is telling out of these 4 statements, you need to find the incorrect statement. So
Yes.
he's telling that the shortest and longest link lengths cannot be less than the sum of the remaining 2 link lengths. That means cannot be less than, it should always be greater than.
Greater.
So is it wrong or correct?
Wrong, sir. Wrong statement.
Wrong statement. Okay,
Yes.
we'll see the about other statements too. Inversions of a mechanism are created by fixing different links one at a time. Yes or no? Is it correct or wrong?
Different links, different times.
Yeah,
Which is also
different
wrong.
links one at a time. One at a time. One ఒక టైం కి ఒకటి లింక్ ని ఫిక్స్ చేస్తేనే కదా. డిఫరెంట్ లింక్స్ క్రియేటెడ్ బై ఫిక్సింగ్ డిఫరెంట్ లింక్స్ వన్ ఎట్ ఏ టైం అన్నాడు వాడు అనమాట. ఒక్కొక్కసారి ఒక్కొక్క లింక్ ని ఫిక్స్ చేస్తే దాని ఇన్వర్షన్ ఆఫ్ మెకానిజం అంటాము అనేసి అంటున్నాడు. అన్ని లింక్ ని ఫిక్స్ చేస్తే అక్కడ మెకానిజం ఉండదు కదా.
డిఫరెంట్ లింక్స్ వన్ ఎట్ ఏ టైం.
డిఫరెంట్ లింక్స్ వన్ ఇచ్చాడు కదా అక్కడ.
ఓకే.
ఒకేసారి అన్ని లింక్స్ ని ఫిక్స్ చేస్తే అది మోషన్ ఏమి ఉండదు కదా.
ఎస్ సార్. అవును.
అర్థమైంది కదా. ఓకే. సో ఈజ్ ఇట్ కరెక్ట్ ఆర్ రాంగ్?
కరెక్ట్ సార్.
యా కరెక్ట్. So Geneva mechanism is an intermittent motion device. Geneva you don't have. So I'll tell you in next chapter we are going to discuss this. So basically it is also correct. So Grubler's criteria assumes mobility of a planar mechanism to be 1. Yes or no? Kurzbach equation and Grubler's equation. What
yes,
is
sir.
the difference? What Grubler did?
F equal to 1.
Yeah. And also he assumed another what?
H, higher pair equal to 0, sir.
Higher pair is equal to 0 and F is equal to
1.
Okay,
Yes,
this
sir.
is what he did. So all the statements are correct except the first statement, which is wrong. So your answer is
Option
what? Option
A, sir.
A.
A.
Option A is your correct. And this question asked for 2 marks. Okay, and next. In a 4-bar linkage, S denotes the shortest link length, L is the longest link length, P and Q are the lengths of other 2 links. At least one of the 3 moving links will rotate by 360 degrees. At least one of the 3 moving links. So, in a mechanism, how many number of links he is telling? So, 4 bar, 4 links, right?
Yes, sir.
Okay, so in these 4 links, so one link is fixed. So link number 1 is fixed. So link number 2, 3 and 4 are the moving links. So what he is telling, at least one of the 3 moving links will rotate by 360 degrees. So oka link 360 degrees rotate aval at least. Okay. So what is the condition and adged? So S plus L, what is the condition? S plus L
Should less than or equal to P plus Q.
should less than or equal to P plus Q. This is Grashof law. Okay. So
Yes,
next
sir.
time వచ్చాడు S plus L is greater than P plus Q. ఇప్పుడు ఇది కండిషన్ అయితే ఏంటి, ఏ లింక్ ఫిక్స్ చేసినా యు ఆర్ గోయింగ్ టు గెట్ రాకర్ మెకానిజం. yes or no?
Yes, sir.
So he is giving some D statement which is completely incorrect. L is not any L is the longest link. Okay, so this is D also wrong, and B is also wrong, and C, what is C? S plus P, this is also completely wrong. So what is remaining? The first link, which is S plus L, is less than or equal to P plus Q. Have you got it?
Yes, sir. Got it.
Okay, so this is another question, and in the GATE 2006 only another question came. The number of inversions for a single crank. So here he forgot single slider crank chain. How many inversions you have in single slider crank mechanism? How many inversions?
4, sir.
Yes,
4.
4 inversions. 4 links are there. So if I fix one link, I'm going to get one mechanism. Yes, we got 4 mechanisms, 4 inversions. Got it? So this is correct. Next, coming to this particular question, and this question they have asked for 2 marks. Oh, sorry. Sorry. Yeah. What happened? Sorry, ma. You know, sometimes this particular, yeah. So if you see this particular question, they have asked for 2 marks. Now you just tell me how to solve this particular. What is this mechanism? You people there?
Crank and slotted lever mechanism.
Yeah, a simple quick return motion mechanism. Okay, it is a crank and slotted lever mechanism. So he's telling that a simple quick return mechanism is shown in the figure. The forward to return ratio, that means your beta by alpha. Forward to return ratio of the quick return mechanism is 2:1. That is QRR. So he is telling that 2 divided by 1, which is equal to 2. Okay, 2. If the radius of the crank O1P, so O1P is nothing but your crank. So how much he gave? 125 mm. So here I'm taking as crank is 125 mm. Next, then the distance D. What is the distance D? This is nothing but the coupler or connecting rod. So what is connecting rod length? So he is asking you to find out connecting rod length between the crank centers to the lever pivot center point. Should be how much? So you need to find out this. He gave crank length. You need to find out this. So how you can find out, ma? What is the quick return ratio? Hello?
Sir.
What is quick return ratio? From where we are taking quick return ratio? Which points? What are the points? Do you remember the figure,
Mm,
or shall I draw the figure?
yeah.
So this is my coupler point. This is my slotted bar. So this is my crank where slotted bar is connected. So my slotted bar is going to is going to oscillate. Okay. So maximum points will be, so I'll just draw the maximum points. I'll draw this maximum points. I don't know whether you remember these points or not. These are the two extreme points. So where my crank will be perpendicular to the slotted bar motion. So this position I took as B and this position as B1. Okay. And the angle here we took as alpha, and here the angle we took as beta. The semi angle here it is alpha by 2. Okay, this is the semi angle alpha by 2. Now you can take this particular triangle, so O, and this is say O dash. So you can take triangle O dash B. So what is the angle here? Alpha by 2. And this is a right angle triangle. Yes or no? Hello?
Yes, sir.
Yes or no? Yeah. So this is O dash is the O dash is the length. What is the length, ma? O dash is nothing but coupler length
Hypotenuse.
or coupler length. Yes or no?
Yes, sir.
Coupler or connecting rod. And OB is nothing but what? Crank. Okay. Now apply the rule. So your base is nothing but your O dash B. Now just tell me, shall I take cos beta or cos alpha by 2 or sin alpha by 2? Hello?
Sin alpha by 2, sir.
Yeah. Okay. If you are taking sin alpha by 2, which is equal to what? Opposite side.
Yes, sir. OB crank by O dash.
OB is nothing but you don't know, right? O dash B you need, na? So what you are going to take? Cos
Cos.
alpha by 2 is equal to O dash B divided by what? O dash O.
O.
Yes or no?
Yes, sir.
Can I write down like this?
Yes, sir.
So now from this equation, that is beta by alpha is equal to 2. Can you find out what is beta value with respect to alpha? So beta is equal to twice of alpha. Yes or no? Ma,
Yes.
you please let me know. Yes or no?
Yes, sir. Yes.
Yes. What is alpha plus beta? Alpha plus beta is equal to 360 degrees, right?
360.
Yes or no? Yes, 360 degrees. So here beta is equal to 2 alpha. So combine, if I substitute this value here, what you're going to get? 3 alpha
Alpha.
is equal to 360 degrees. Yes.
Yes,
So
sir.
alpha is equal to 360 divided by
3.
So what you're going to
120.
get? Alpha value. Yes, 120 degrees. So here alpha is equal to 120 degrees. So use your calculator, substitute here alpha value. So cos 120 degrees divided by 2. So it becomes 60 is equal to, what is O dash B? O dash B is crank. What is the length of the crank he gave?
Oh.
Crank length is 125. ఇచ్చాడు కదా ఇక్కడ question లో.
Yes, sir. 125 mm.
Yeah, 125 divided by, we don't know about the coupler length, so I'm just substituting D value because he gave D. So what is the value of cos 60? Cos
Root 3 by 2.
root 3 by 2,
2.
which is equal to 125 divided by D. So D is equal to 125 into
Sin
2
30.
divided by root 3. What is the value you're going to get? What is cos 60
Sir,
value?
cos 61 by 2, sir.
That's what I'm
Yes, sir. Yes, sir.
Cos 60 is 1 by 2.
Mm.
Okay, so what is the value of D now? 250 mm. That's it, right?
250 mm.
Ante kada? 1 by
Yeah,
2 is equal to 125 by D. D is equal to what? 125 into 2. Yes or no?
sir.
Do you have the option? Do you have the option here? 250?
Option D, sir.
Very good. So you bagged 2 marks. How much time you took? Hardly 2 minutes, right? 2 to 3 minutes to solve the problem.
Yes, sir.
That's it. So that's why if you practice now, you are going to get. Okay. So next question. So he's asking you to match the following. Okay. So just match the following. So type of mechanism he gave and the motion achieved he gave. So P, Q, minute. So P, Q, R, S. What is P? Scott-Russell mechanism. What is the Scott-Russell mechanism? Scott-Russell
Don't-
mechanism.
You don't know, sir. Scott Russell.
Okay. So Geneva, I'll explain, ma. So don't worry. Scott-Russell, these are the two things which is not there. I'm going to explain you Scott-Russell and Geneva. Scott-Russell is nothing but the straight line mechanism we going to have. 1 minute. So Scott-Yoke, I hope you know this particular Scott-Yoke, right?
Yes,
Scott-Yoke
sir.
mechanism. Now itself we have discussed Scott-Yoke. Which mechanisms you are going to get? Scott-Yoke.
A moment. Yes, to quick return, sir.
Pardon?
Quick
Scott-Yoke.
return.
Scott-Yoke ఎలా ఉంటుంది? Okay, offset slider crank mechanism. Offset అంటే ఏం లేదు. సింగిల్ స్లైడర్ క్రాంక్ మెకానిజం ఉంది కదా?
Yes, sir.
సింగిల్ స్లైడర్ క్రాంక్ మెకానిజం లో లైన్ ఆఫ్ యాక్షన్ ఏదైతే స్లైడర్ ఉంటుందో దే ఆర్ గోయింగ్ టు కీప్ సపోజ్ 1 minute. So this is my slider motion. Okay, and they are going to place your crank at some end. So this distance is nothing but your offset. Okay, so when I'm going to place this, you are going to get quick return motion mechanism. That is the what inversion of what slider crank mechanism. Yes or no? Avuna kada amma?
Yes, sir.
బేసికలీ హియర్ ఇన్ ఇన్వర్జన్స్ ఇక్కడ మీరు చూసినట్లయితే ఇక్కడ ఇన్వర్జన్స్ ఏమున్నాయి? స్లైడర్ క్రాంక్ మెకానిజంలో స్ట్రైట్ లైన్ మోషన్ కాదు. ఆ స్ట్రైట్ లైన్ మోషన్ చెప్పాను కదా, సింపుల్ మెకానిజమ్స్. I'll tell you that those straight line motion mechanisms a little bit later. So basically Scott-Russell mechanism and Geneva mechanism, these two comes under the second part and I'm going to explain you. But slider crank mechanism, you are going to get inversion is quick return motion mechanism. And also Scott-Yoke mechanism, you don't know 1, 3, 4, but here you know only one option. Okay, sir, can I solve the question? Okay, so R is 2, right? So under R 2, if you see option number A, R is equal to 1, which is wrong. Okay, you can take odd out of got it. Illa kuda manam cheyochu annamata. So B lo kuda R 4 undi, so which is wrong, and D lo kuda R 1 undi, which is wrong. So only option C you have left with, and this option C is correct. Illa kuda manam cheyochu, manaku konni anni teliyalani ledu. But మనకు వచ్చిన వాటిలో కూడా if you use some common sense you can crack gate. Yes or no? అర్థమైంది కదా?
Yes, sir. అర్థమైంది.
Yeah. So the last question from previous year's gate. So the length of the links of a 4-bar linkage with revolute pairs only are P, Q, R and S units. Given that P is less than Q is less than R is less than S, which of these links should be fixed one for obtaining a double crank mechanism? సో డబుల్ క్రాంక్ కావాలంటే ఏ లింక్ ని ఫిక్స్ చేయాలి అని వాడు అడుగుతున్నాడు. అన్నిటికన్నా చిన్న లింక్ ఏంటిది?
P, sir.
ఎస్. ఇప్పుడు ఏ లింక్ నేను ఫిక్స్ చేస్తే నాకు డబుల్ క్రాంక్ మెకానిజం వస్తుంది? 4 bar mechanism లో which link if I fix you are going to get double crank mechanism?
No.
మర్చిపోయారా? So this is the link. So if I fix the shortest link, I have shown you the mechanism also. If I fix the shortest link, you are going to get what? Double crank mechanism. ఇక్కడ shortest link ఏది?
P, sir.
Pardon? P. Very good. So the option is what? A. So I hope you got it. So these are the questions from the previous year's gate. So now can you solve the questions now? Whatever the questions you are going to get from the first unit. Hello?
Yes, sir.
Yes? Yeah, okay. So I
Sir,
hope చెప్పనా.
ఈ PDF ఏమైనా ఉందా సార్?
Yeah, I'll share.
అంటే ఆ ఫిగర్ ఒకసారి ఇంకోసారి చూసుకుందాం.
I'll share those things. No problem.
Yes,
But
sir.
you people also need to write parallelly while I'm explaining. Okay? So
Yes,
మీరు రాస్తుంటేనే మీకు అర్థం అవుతూ ఉంటుంది, లేదంటే ఇబ్బంది పడుతూ ఉంటారు అన్నమాట. Okay, no problem. I'll share the notes with you. So
Yes, sir.
I hope now you got this particular topic. Can I move to the next topic, which is another important?
Yes,
Yes?
sir. Yes, sir.
Yes. So the next topic is simple mechanisms. Velocity analysis. So 1 minute. There's a question here. So I hope can you take some 2 minutes? I'll just have my water. I'll drink some water and I'll come.
Yes, sir. Okay, sir.
Yeah. So
Okay.
మైక్స్ ఆన్ చేసి పెట్టుకోండి, నేను వచ్చి పిలిస్తే పలకడానికి.
Okay, sir.
Yeah. హలో, ఉన్నారా అమ్మా? స్టార్ట్ చేసేదా?
Okay, sir.
Yeah. So we'll discuss now about the velocity analysis. I hope you know the difference between angular velocity and linear velocity. Okay. So this is unit 2 or topic 2, which is velocity analysis. Okay. So here in this particular topic, so we can solve the problems by using two approaches. We have two approaches. So one is instantaneous center method. Instantaneous center method. The other is relative velocity method. relative velocity method. Okay, now just tell me first, before entering into instantaneous center or relative velocity method, can you please define me what is velocity? Can you define velocity?
The rate of change of speed.
Very good. Rate of change of speed.
Yes.
What speed? Speed is a scalar quantity. Velocity is a vector quantity. Both have same units. Rate of change of displacement.
Dis-
Okay.
Sorry, sir. Yes.
Yeah, rate of change of displacement. That means with respect to time, if my velocity is changing, then I'm going to call it as, sorry, with respect to time, if my displacement is changing, then I'm going to call it as velocity.
Velocity.
Okay, so it is dt, sorry, a ds by dt. This is nothing but a velocity. What about angular velocity? Rate of change of angular displacement. Okay, so d theta by dt. This is nothing but your angular velocity, d theta by dt. Got it? These are about velocities. And now first we'll discuss clearly about instantaneous center method. Do you remember instantaneous center method from your BTech? Now in which year you people are there?
3 1, sir.
Okay, I think in the last year itself, in the second year,
2-1, sir. 2-1.
in 2-1 you people have studied. Okay, so what is instantaneous center method? అయిపోయిందా?
Rotation with respect to 1 point, sir, at particular point.
Rotation with respect to 1 point.
Uh,
Okay, I'll tell you one thing. So basically this method has pioneered. Okay, we are going to call as Sir Aaron Holt and Kennedy. So basically in English speaking countries, they'll call as Kennedy's theorem, and in German speaking countries they're called as Ironhold theorem. Okay, in India we are going to call it as Ironhold Kennedy's theorem. So basically in the year 1872, Ironhold is a German scientist. So he's German, and this fellow is from England, and at the age of 21 he like demonstrated this particular method, instantaneous center method. What exactly this particular demonstration they did? So basically instantaneous center, or simply I can call it as IC, is a point. It is nothing but instantaneous center we call it as, and it is simply a point. So now what is this particular point? The question arises is, what is this point, or what point it is? This is the question. This point is basically is in general motion. It is in general motion. So you may call, sir, what is this particular general motion? So general motion is nothing but it is neither in pure translation nor in pure rotation. Okay, it is a combination of rotation as well as translation. I don't know why this 1 minute. Yeah, so general motion is nothing but combination of rotation plus translation. So what they observed is, I'll give you some two instances. Both you may think like both are same, but there is some difference. Okay, minute difference in both these cases. The first case is, so please observe, please understand what I'm telling. The first case. In the first case, so I'm just taking a line. So you can say this as a line AB. This is point A and this is point B. This may be a line or any some stack, whatever may be. So how many points are there? There are infinite points are there. So you can mark infinite points. And on these infinite points, or consider here how many points I have marked? 5 points. And you and your friends were sitting on these particular points. So I hope you got it. So on these points, you and your friends were sitting. Okay, now, so when you are going to observe pure rotation, so you have AB, this particular stick is in stationary. Okay, now on the stationary stick at 5 different points, you and your friends sat. Now just tell me, when you are going to observe pure rotation, when you are going to feel pure rotation, or else simply I can say, suppose here my velocity vector, this is my velocity vector. This velocity vector is at present is perpendicular, that means at 90 degrees to this particular line. This is my velocity vector. So when the velocity vector is perpendicular, please do remember this particular point. Wherever you sit on a line which is perpendicular to the velocity vector, here your stick AB is exactly perpendicular to the velocity vector. So you will observe a pure rotation at this particular point. So wherever you sit on a line perpendicular to the vector, velocity vector, you will observe pure rotation. So I hope you got it. The first case. Have you got it? The first case. The second case. In the second case, suppose a body is rotating with respect to some center of rotation. So example, so this is origin or point O and a link. So this is this particular link. So you have applied some angular velocity, and this particular link, say point O and B. So this point OB is link to, with respect to link 1, I have given some angular rotation, angular velocity, and it is going to rotate about point O. So this is the rotation. Okay, so this is the rotation. And now, so if you want to observe pure rotation, always velocity vector will be perpendicular to this particular link. So at present here is my velocity vector V. Okay, so when this particular link is moved to this particular point, so here my velocity vector will again be perpendicular to the particular link OB. So here OB dash. So they observed these two cases. So I'll write here. So in rotation of a link, anywhere velocity vector will be perpendicular to link OB. So they have what combined these two cases, and they have derived one solution. What is the solution? So now, so I hope you got these two cases. So what I'm doing is I'm taking a link. So this is my link. This is link and points are A, B. So these are microscopic observations. Ma, you people there? Hello?
Yes, sir.
Yeah.
Yes, sir.
These are microscopic observations after time t interval. So what is this? I took a link which is AB after delta t time. T is equal to t. Okay, this is the position. And after, so this particular link has moved. So microscopic observation, na? So I'm just tilting this particular line. So this is my A dash, the position is A dash, and this is B dash. So at time t is equal to t plus dt. Okay. So now what I'm going to do is, so I'll just join these 2 points. What are the points? I'll join A to A dash. I'm joining the points what? A to A dash and B to B dash. Why I'm joining is the position from A, it has been changed to A dash. From position B to B dash, it has changed. So what I'm going to do is I'm going to draw a perpendicular lines now with respect to B to B dash. So this may be the perpendicular line. And also I'm going to draw a perpendicular line with respect to A dash. So these are going to join. Now these two perpendicular lines are going to join at one point. So here is the point. This is the point. And this point is nothing but I. So what is the meaning of this is, so if you people are going to stand at point I, okay, at an instant, so the link AB, it has changing from this particular position to A dash to B dash, A dash B dash. So when it is moving from AB to A dash B dash, so if you stand at point I, you are going to observe pure rotation. I hope you got it. So apart from I, if you stand any other points, so in the space you have infinite points. If you stand any of the points, you won't see a pure rotation. But only if you stand at point I, you can observe a pure rotation. Similarly, suppose after another time interval, this point has moved, this link has moved from A dash to A double dash and B dash to B double dash. Now what you're going to do, you need to join points A dash to A double dash. So I'm just joining A dash to A double dash. Similarly, I'm joining B dash to B double dash. So again, you need to draw a perpendicular lines with respect to this link, this point, and also to these points. Somewhere here you are going to get this point, say this point is I2. Earlier it was I1 and this is I2. Okay, so that means here my instantaneous centers, that is the point I is changing while my link is moving. Okay, so now observe carefully. I'm going to give you some important definitions also here. Okay, so if I join all these I centers, that means I1, I2, I3, I4, I5 and so on. Whatever the points, infinite points I'm going to get. So locus of all I centers. 1 minute. Locus of all I centers is called as centrode. This is very, very important in gate perspective. Locus of all eye centers is called as centrode. Okay. Now these eye centers. Now just tell me what is the difference between a center point and an axis. Axis is nothing but an imaginary line. Center is also an imaginary line, the imaginary point. Center point is nothing but with respect to what where you can see a pure rotation or motion. So 1 minute, I don't know. Can you see this particular? Yeah, I'm getting the, yeah. Why I can't. Hello?
Sir, చెప్పండి.
No problem. My end, I'm getting some problem with the whiteboard. I can't move my mouse. Are you facing the same problem? Okay, give me a minute, ma. I'll just close it and I'll reopen it.
Okay.
Yeah, it may take for a while, 2 minutes or 1 minute. And now Raghunath and Vasudej, like if you have any doubts, please. Meanwhile, we'll interact, ma. Why to waste time? So we'll interact. Vasudej, do you have any doubts?
No, sir.
No, now clear everything, whatever I'm just explaining.
Yes, sir. Yes, sir. Understanding, sir.
Yeah. What about Raghunath? Do you have any specific doubts?
No, sir, no doubts.
No doubts.
No doubt.
సో లైక్ ప్రాబ్లమ్స్ ఇంకా ఎలా ఇస్తారు, ఏంటి, ఎలా ఫ్రేమ్ చేయొచ్చు, ఏమైనా డౌట్స్ ఉన్నాయా అలా అయినా, లేదంటే గుడ్డిగా వింటూ వెళ్తున్నారా? ఇంకేమన్నా
అంటే ఇంకేమన్నా మోడల్స్ లో సమ్స్ ఉంటే ఒకసారి ఆ గేట్ కాకుండా అలాంటి సమ్స్ ఏమన్నా ఉంటే అవి కూడా ఎక్స్ప్లెయిన్ చేయరా సార్?
అంటే లైక్ అపార్ట్ ఫ్రమ్ గేట్ యు వాంట్ క్వశ్చన్స్?
అపార్ట్ ఫ్రమ్ అలాంటి మోడల్స్ ఎక్కడన్నా బయట ఉంటే సమ్స్ అలాంటివి కూడా ఎక్స్ప్లెయిన్ చేయరా సార్?
ఓకే, సో ఫస్ట్ యూనిట్ లో నుంచి ఐ హ్యావ్ ఎ లైక్ బుక్ విచ్ యూ కెన్ ఫైండ్ అవుట్ ఇన్ ఇంటర్నెట్ ఆల్సో, ఎస్కే మోండల్ సార్. సో దాంట్లో ఐఏఎస్ క్వశ్చన్స్, ఐఏఎస్ క్వశ్చన్స్ కూడా ఉన్నాయి. ఇఫ్ యూ వాంట్ ఐ విల్ టేక్ దోస్ క్వశ్చన్స్ ఆల్సో.
అంటే అలా కొంచెం మోడల్స్ ఇలాగే వచ్చేలాగా గేట్ లాగే ఉండే మోడల్స్, వాటి మీద ఉండే ప్రాబ్లమ్స్ ఎక్స్ప్లెయిన్ చేయండి సార్.
సో ఓకే మా జస్ట్ అండర్స్టాండ్ వన్ థింగ్. సో మీకు ప్రాబ్లమ్స్ ఏవైతే ఉన్నాయో అవి గేట్లోనే అడుగుతారు, ఓకేనా? ఇంజనీరింగ్ సర్వీసెస్లో, ఐఏఎస్లో, ఐఏఎస్లో అంటే అడ్మినిస్ట్రేటివ్ సర్వీసెస్లో ప్రాబ్లమ్స్ అడుగుతారు కొంచెం, బట్ థియరీ ఎక్కువ ఉంటుంది. సో మీరు ఒకవేళ లైక్ స్టేట్ సర్వీసెస్కి ప్రిపేర్ అవుతున్నారు అనుకోండి, స్టేట్ సర్వీసెస్ తెలుసు కదా? హలో, ఏపీపీఎస్సి, మా ఇక్కడేమో టీఎస్పీఎస్సి ఇప్పుడు అయింది. ఇదివరకు ఏపీపీఎస్సి ఎగ్జామ్స్ ఉండేవి కదా, లైక్ అసిస్టెంట్ ఇంజనీర్, ఏడబ్ల్యూ, ఏఈ, వీటికి ఒకవేళ మీరు ప్రిపేర్ అవ్వాలనుకుంటే మాక్సిమం థియరీ క్వశ్చన్స్ అడుగుతారు. మోడల్స్ అంటే అవే. సో ఇక్కడ మీకు ఎన్ని ఇన్వర్జన్స్ ఉన్నాయి, థియరీ క్వశ్చన్స్ కూడా ఉన్నాయి కదా, సిమిలర్గా అలా అడుగుతారు. అంటే మీకు ఏమైనా థియరీ ఆస్పెక్ట్ లో కూడా కావాలా, అంటే లైక్ డిస్క్రిప్టివ్ లో చెప్పాలా?
అది అలా కాకపోయినా మామూలుగా గేట్ లో తిరిగి వచ్చే మోడల్స్ అయినా పర్లేదు సార్.
లైక్ గేట్ లో థియరీ క్వశ్చన్స్ ఏవైతే ఉన్నాయో అవి చెప్పాను కదా. ఓకే, సో ఇంకా ప్రాబబిలిటీ ఇంకా ఎందుట్లో అడగచ్చు అలా కూడా?
అలాగే సార్, అలాగా. ఒకవేళ ఇంకొక పార్ట్ లోంచి ప్రాబిలిటీ ఏమైనా ఉంటే వాటి మీద ప్రాబ్లమ్స్ చెప్పండి సార్.
Yeah. Okay, sure. I'll tell. I'll explain. So first
సార్
unit
ఇంకొకటి
గురించి చెప్తాను.
అది ఇప్పుడు ప్రజెంట్ మీరు చెప్పేది ఆల్రెడీ మాకున్న సిలబసే కదా సార్? అంటే ఆల్రెడీ మీరు చదువుకున్నది సెకండ్
Yeah.
ఇయర్ లో.
Yeah.
కానీ గేట్ లో అపార్ట్ ఫ్రమ్ మై సిలబస్ ఇంకా వేరే సిలబస్ కూడా ఉండదంట కదా?
వేరే సిలబస్ ఇప్పుడు మీరు ఏదైతే చదువుకున్నారో ఆ సిలబస్ లో నుంచే ఇప్పుడు మీరు కామ్ లో కొంచెం చదివారు, సారీ కామ్ చదివారు, డామ్ చదివారు, అవునా? గేట్ లో కామ్ లో మీరు ఏదైతే చదివారో అందుట్లో కొంచెం పార్టే ఉంది. ఎగ్జాంపుల్, మీకు కామ్ లో మీరు 5 యూనిట్లలో చెప్పేది ఫస్ట్ సింపుల్ మెకానిజమ్స్ చదివారా? నాకు తెలిసి చదివిన వాటిలో డిగ్రీ ఆఫ్ ఫ్రీడమ్ గురించి ఎక్కువ చదువుండరు. డిగ్రీ ఆఫ్ ఫ్రీడమ్ ప్రాబ్లమ్స్ మీద ఎక్కువ ఉండవు. మీ ఇది ఏదైతే
ఓన్లీ డిగ్రీ ఆఫ్ ఫ్రీడమ్ మీద ఓన్లీ థియరీ సార్ ఉంది.
ప్రాబ్లమ్స్ లేవు. బట్ ఇక్కడ మనం ప్రాబ్లమ్స్ చేసాం, చాలా ప్రాబ్లమ్స్ గుర్తున్నాయా మీకు ఇదివరకు? అదొకటి అడిషనల్. ఓకే, నెక్స్ట్ వచ్చేసి వెలాసిటీ డయాగ్రామ్స్, యాక్సిలరేషన్ డయాగ్రామ్స్. సో మీకు ఏదైతే సిలబస్ ఉందో ఆ సిలబస్ ఇక్కడ ఉంది, వేరేదేం లేదు అడిషనల్ గా.
కానీ గేట్ లో ఇంకా ఎక్స్ట్రా సిలబస్ ఉన్నదంట కదా సార్?
ఎక్స్ట్రా సిలబస్ మన సబ్జెక్ట్ లో అయితే లేదు, ఇంకా తక్కువే ఉంది. ఎందుకంటే థర్డ్ యూనిట్ ఏదైతే మీకు లైక్ సిలబస్ ఉంటాయి కదా, ఏది ఆటోమొబైల్ హూక్ జాయింట్ కానీ డేవిస్ ఎకర్మన్ స్టీరింగ్ గేర్ మెకానిజమ్స్ మీరు చదువుకున్నారు, గుర్తున్నాయా? స్ట్రైట్ లైన్ మోషన్ మెకానిజమ్స్ అవి ఎక్కువ అడగడు గేట్. ఓకే, అండ్ క్యామ్స్ గేర్స్ ఏవైతే మీరు చదువుతారో అవి కూడా ఉన్నాయి గేట్ లో, సేమ్ సిలబస్. ఇంకా క్యామ్స్ గురించి ఎక్కువ అడగడు గేట్ లో, బట్ స్ట్రెస్ ఎక్కువ గేర్స్ మీద చేస్తాడు అనమాట, హైయర్ పేర్స్ లో నుంచి. లోవర్ పేర్స్ లో నుంచి వెలాసిటీ డయాగ్రామ్స్ ఇంకా ఫస్ట్ యూనిట్ డిగ్రీ ఆఫ్ ఫ్రీడమ్ మీద తీసుకుంటాడు. ఓకే, అండ్ మీకు వైబ్రేషన్స్ గురించి ఉందా మీకు?
వైబ్రేషన్స్ అంటే అది ఇప్పుడు లేదు సార్.
ఓకే, డైనమిక్స్ ఆఫ్ మెషినరీ అయిపోయిందా, అవ్వలేదా మీకు? ఇంకా
అయిపోయింది సార్ వైబ్రేషన్స్.
కాకపోతే
అది ఆన్లైన్ లో చెప్పేసరికి కొంచెం ఏదో పైపైన చెప్పేశారు ఎగ్జామ్ హడావుడిలో.
ఓకే. సో మనం ఏంటంటే ఈ డీటెయిల్ గా ఇక్కడ నేర్చుకుంటాం అనమాట. మీకు గేట్ సిలబస్ కి సారీ గేట్ ఎక్స్ప్లెనేషన్ కి లైక్ కాలేజ్ లో ఎక్స్ప్లెనేషన్ కి ఇక్కడే డిఫరెన్స్ వస్తుంది. ఇక్కడ ఏంటంటే గేట్ దేని మీద టాపిక్స్ వస్తాయో వాటి మీద స్ట్రెస్ ఎక్కువ పెడతాం అనమాట. ఓకేనా? సో ఈ సిలబస్ అంటే మనం గేట్ అనగానే వేరే సిలబస్ ఉంటది, మనం చదువుకొని ఉంటది అనుకోవద్దు. గేట్ అంటే ఏంటిది? డూ యు నో ద ఫుల్ ఫామ్ ఆఫ్ గేట్? హలో
సార్,
గేట్ ఫుల్ ఫామ్ తెలుసా?
గ్రాడ్యుయేట్ యాప్టిట్యూడ్ టెస్ట్ ఇన్ ఇంజనీరింగ్.
వెరీ గుడ్. ఆప్టిట్యూడ్ అంటే మీనింగ్ ఏంటి?
క్రిటికల్ థింకింగ్ సార్.
సో
రీజనింగ్ సార్, రీజనింగ్
గ్రాడ్యుయేట్ ఆప్టిట్యూడ్ అన్నాడు వాడు, అవునా? సో మీరు గ్రాడ్యుయేషన్ లో ఏవైతే చదువుకున్నారో వాటి గురించి అడుగుతాడు, లేని ఎందుకు అడుగుతాడు వాడు? అర్థమైందా నాన్న రఘునాథ్?
అర్థమైంది సార్. కాకపోతే మా సిలబస్ వేరు, అంటే వేరే ఇంజనీరింగ్ కాలేజీలో వేరే సిలబస్ ఉంటుంది కదా సార్, అంతా ఒకటే ఉండదు.
మాక్సిమం స్మాల్ చేంజెస్ ఉంటాయమ్మా, బట్ ఎవ్రీథింగ్ విల్ బి సేమ్. నేను చెప్పే మీకు సిలబస్ అంతే కంప్లీట్ గేట్ రిలేటెడ్, బికాజ్ ఐఎమ్ స్టూడెంట్. పాస్ట్ గేట్ ఇయర్స్ అవన్నీ నేను చదివే వచ్చాను ఇక్కడికి. ఓకే, ట్రాక్ చేసి. అర్థమైంది కదా? ఐ హోప్ లైక్ షల్ వి మూవ్ ఆన్ టు ద సబ్జెక్ట్?
Yes sir.
Yeah.
Yes sir.
It got rectified. Okay, so this point is very very important. Locus of all eye centers is called as what? Centroid. Similarly, locus of all eye axis. So suppose if I take an example here, so O is nothing but the center. Suppose if I add this particular circle, so if I add thickness, what happens? It becomes a cylinder. Yes or no? So ఇప్పుడు ఈ సెంటర్ ని కూడా if I add some thickness, okay, so it forms an axis. We call that as an axis. Axis is nothing but imaginary. So if I what? Locus of all eye axis. Next, locus of all eye instantaneous center axis is called axode. So these are the points which in your what engineering colleges you haven't studied these things. So locus of all eye centers is called centroid, and locus of all eye axis is called axon. Okay, so for 1 mark questions they may ask you these questions. Got it? So coming back to this eye centers, microscopic observations. So you need to understand about one thing, like what is now the relation between angular velocity and linear velocity. So here omega of AB. So AB is nothing but the link. So this particular link, angular velocity, how I can find out? So from AB to position A dash B dash, so I can see I can observe pure rotation when I'm standing from I. So here I1 becomes my like a reference point or center of rotation. So if I want to take this particular point I1, so how I can find out this angular velocity? Can you tell me what is the relation between linear velocity and angular velocity? So velocity is equal to r omega, right?
Equal to r omega.
R omega. So here I can say here V by R. Now just tell me what is this R? R is nothing but the radius of rotation. So axis nunchi entaithe length untundo, that length we are going to take. Yes or no? So here you may take any of the points here. So you can take infinite points. So ikkada I can write name C, D, E, F, G. You can find out velocity of point C, velocity of D, velocity of C, F, G, whatever may be. Okay, so here, but what about the radius r? So if you are taking, if you want to find out velocity of point C, okay, C becomes your reference. So from C to I is your distance you need to measure. So velocity of C is equal to r is nothing but the radius. So the distance between I1 to C. So from here I1 to C, whatever the distance you are going to get, you need to consider that particular distance and into omega of AB or whatever may be, because angular velocity of that link you may take CB or DE, one and the same. Okay, so omega AB now I can write, which is equal to V of C by I1 C. Similarly, you may take the ratio to find out omega of AB, velocity of D divided by I1 D, that is equal to velocity of E divided by I1 E, and so on and so forth. This is nothing but angular velocity theorem. I'm going to explain you that in detail. So in this manner, here I'm going to find out velocities and angular velocities. Okay. So what I said, the link AB at this particular instant is in general motion. So as I said, what is general motion? It is a combination of rotation and translation. Okay. So one will ask you to write down the definition or definition of instantaneous center. So in general motion, I'm just writing this. You may please note down in your notes. So in general motion of a link, in a mechanism, is neither in a pure translation and rotation. Neither in a pure translation and a rotation, neither in pure translation and rotation. It is a combination of both translation and rotation. Combination of both the translation and rotation. Which we normally say, the link is in general motion. But any link at any instant, at any instant. Can be assumed to be in pure rotation. With respect to the point in space is known as, basically it is a definition, is known as instantaneous center of rotation. Center of rotation, or it is also called as virtual center. See, in some questions they may ask you virtual center, so don't get confused, both are same. So virtual center or instantaneous center of rotation. So centroid and axoid. Now I'll ask you a few questions, ma. Can you able to answer? So first I'll give you some 1 minute. So I'll give you some motion between the links. So you have to tell me what will be the centroid and what will be the axoid. So if at all it is in general motion, what will be the centroid? Hello, you people there?
Yes, sir.
Okay. If you are unable to tell, otherwise tell this. Suppose if at all it is in pure translation, if the link is in pure translation, now what will be the centroid? Okay, centroid ante ఏమని చెప్పానమ్మా? Locus of all eye centers, na?
Yes, sir. I said.
So pure translation లో ఉంటే ఏదన్నా లింక్, దాని యొక్క సెంట్రోడ్ ఎట్లా ఉంటుంది, ఎలా కనిపిస్తుంది మీకు? అర్థం కాలేదా?
నో సార్.
Give me a minute, ma. అక్కడ ఉంది. Sorry. Okay. So suppose when a link is in pure translation, so example, say A and B. Okay. Now, if at all it is in pure translation, it is moving. Okay. Suppose if you take a point B, so the locus of this is like this. So it is a straight line. Now, what is the definition I said? Whatever may be the link, it is in general motion or if at all it is in general motion, that means it is in translation and rotation both. Any link we can say that we can be assumed to be in pure rotation, okay, with respect to the point in space. Now just tell me, can you define a straight line? Can you define a straight line? Infinite radius. Do you know that? మా తెలుసు కదా, స్ట్రైట్ లైన్ ఏంటి? ఇన్ఫైనైట్ రేడియస్ ఆఫ్ రొటేషన్. ఓకే. సో ఇప్పుడు వాడు ఏమడుగుతున్నాడు అంటే జనరల్ మోషన్ లో అంటే ఏంటిది? ఇప్పుడు ఈ లింక్ ఏదైతే నేను మీకు ఎగ్జాంపుల్ ఇచ్చానో అది జనరల్ మోషన్ లో ఉంది. సో AB, A', B', B'. Now if you see, when it has moved from AB to A', B', this is my I1. So when it is moved from A', B' to A', B', my I2 is this. Suppose if I join these points, I1, I2, I3, I4 ఇలా జాయిన్ చేసుకుంటూ వెళ్తే దాన్ని ఏమని చెప్పాను నేను? సెంట్రోడ్ అన్నాను. ఇప్పుడు ఇది ఏ షేప్ లో ఉంది? స్ట్రైట్ లైన్ లా ఉందా? కర్వ్ షేప్ లో ఉందా? వాట్ ఈస్ ద షేప్ యూ హ్యావ్? సర్కిల్ లా ఉందా?
లైన్ సార్.
లైన్ అంటే I1, I2 ని జాయిన్ చేస్తే నెక్స్ట్ I3 సమ్వేర్ హియర్ యు I5. So these are the points. So is it in a line or is it somewhat curve? Uneven curve, yes or no?
Yes, sir.
Centroid is in like curve. Now what about axod? Axod is nothing but the axis, right? So suppose this is my axis I1, this is the axis 3D low. Like this, these are the axis. So if I join all these axes, ela kanipistundi, ela, how you are going to see? A lines అన్నిటిని join చేసుకుంటే వెళ్తే how you are going to look, it is going to look like locus of lines. It's nothing but the curved surface. మా లైన్స్ అన్ని పక్క పక్కన పెట్టుకొని వెళ్ళండి, how you are going to look? It is like a surface, right?
Yes, sir. Curved surface.
Yeah. What about pure translation? When a link is in pure translation, centroid ఎలా ఉంటుంది? Point ఆ line ఆ? How you are going to? It is a line. So
line.
Now here it is a plane surface. Axod will be looking like a plane surface. Suppose when it is in pure rotation, that
Point.
centroid will be very good point. And here axod will be
Circle.
Axod. Cylindrical hole లో cylindrical shaft ని rotate చేస్తూ ఉంటే center ఉంటుంది, చేంజ్ అవ్వదు కదా. Do you know the axis ఎలా కనిపిస్తుంది? Circle ఆ line ఆ? It's a line. అర్థం కాలేదా?
లాస్ట్ ఒక్కటి అర్థం కాదు సార్, లైన్.
ఓకే. సో బేసిక్ గా ఐ సెంటర్ ఏదైతే ఉందో ఐ సెంటర్ ని ప్రొజెక్ట్ చేస్తే వచ్చేదే ఐ యాక్సోడ్, అవునా? సెంట్రోడ్ ని ప్రొజెక్ట్ చేస్తే వచ్చేది యాక్సోడ్, అవునా కదా?
ఎస్ సార్.
దట్స్ వాట్ ద డెఫినేషన్. Locus of all I axis is nothing but
యాక్సోడ్.
Okay, so pure rotation is nothing but what? There is no changing of this particular point O. Suppose this is a link, this link O and B. So link OB is rotating with respect to point O, avuna? So here this is 1 and 2. I center 1 2 is going to locate at this particular point. I12 is not going to change. So ఇది నా సెంట్రోడ్ అయింది. సో యాక్సిస్ అంటే ఏంటిది? If I project my point, okay, so in the top view you can see the axis, yes or no? So if I project this particular center point, ఎలా కనిపిస్తుంది? పాయింట్ ని ప్రొజెక్ట్ చేస్తే how you are going to see?
Line,
right? Yes. So these are very very important for your understanding purpose. Okay, problems. So centroid general motion లో ఉన్నప్పుడు curve లా ఉంటుంది, axod ఎట్లా curved surface. And it all when it is in pure translation, it is centroid is a line, axod is a plane surface. When it is in pure rotation, centroid is a point and axod is a line. I hope you got it. Yes or no?
Got it.
Got it? Okay, shall I move to the next topic now?
Yes sir.
Okay, so we'll discuss about basic instantaneous centers in a mechanism and Kennedy's theorem. Then we'll discuss the next in the coming classes. Okay, so I hope you got today. So we'll discuss a few points of basic instantaneous centers. So we'll discuss about turning pair, sliding pair, rolling pair, and in curved surfaces how these are going to behave. Those things we are going to discuss. Okay, so basic instantaneous centers. Centers in a mechanism. Okay, so just tell me, the first one is a turning pair. So ikkada instantaneous center ekkada untundi? So here I took an example. This is my turning pair and this is link 1 and this is link 2. So I center is nothing but I12 between these two links. So instantaneous of center of link 1 with respect to link 2, or you can also call as I21. So instantaneous center of link 2 with respect to link 1. Okay, so if you are going to fix link 1, so link 2 is going to rotate. Okay, so that particular rotation, at which point if you stand and see, you can observe pure rotation. A point దగ్గర అర్థమైందా?
Center point.
Yes, very good. So this is that particular point, IC. This is my IC. Okay, so turning pairs ఎప్పుడైనా సరే ఎక్కడైతే connection of that particular point ఉంటుందో that becomes your IC. Okay, so it may be called as I12 or I21. So second, I'll take an example of a sliding pair. So this is my sliding pair. So sliding pair, what is the motion? So here I am taking an example of slider. So it is going to slide with respect to this particular surface. This is link 1 and this is link 2. So it has only one motion, yes or no? It can only reciprocate. It is having pure translation. So now just tell me one thing, where my IC is going to lie?
Along the surface line.
Along the surface line. So పాజిటివ్ అండ్ నెగిటివ్ యాక్సిస్ లో మూవ్ అవుతుంది, ట్రాన్స్లేట్ అవుతుంది స్లైడర్ లింక్ 2 విత్ రెస్పెక్ట్ టు లింక్ 1. yes or no?
Yes sir.
Motion is rectilinear, yes or no? Along x-axis rectilinear. Now on so whatever the space is there on the surface, ఎక్కడ నించొని మీరు చూస్తే you are going to observe pure rotation. Pure rotation.
Perpendicular to the lines, sir.
Yes, perpendicular to the motion. Yes or no? Idi perpendicular. Idi direction of the motion. So to this perpendicular line I have drawn, but at which point if I go and stand, I can see pure rotation. At a distance of 3 to 5 minutes I have explained you. How can you define a straight line? I asked you. What he said. How can you define a straight line? It is nothing but infinite radius of rotation, yes or no?
Yes sir.
Yes. So at which point if I go and stand, I can see a pure rotation? At which point?
I point sir.
Pardon?
I point sir. I instantaneous.
That instantaneous center ekkada mark cheyali nana nenu. So I'll give you again, I'll explain you
two lines perpendicular meet together sir.
Okay, see, so this is my perpendicular line. Okay, and this slider is going to slide with respect to link 1 in this direction of motion. So this is the motion, so where my slider is going to move. So basically so to find out whatever the line which is perpendicular to the direction of motion, so from that link, on that link if I sit or stand, so I can observe pure rotation. But I'm asking you, at which distance? Is this particular distance, or this is the distance, or this is the distance, or what is the point? ఎక్కడ కూర్చుంటే నాకు అది ప్యూర్ రొటేషన్ లా కనిపిస్తుంది? దట్ ఈస్ వాట్ ఐఎమ్ ఆస్కింగ్. నా క్వశ్చన్ అర్థమైందా?
Yes sir.
Yeah, tell me, answer. So your motion is, what is your motion? Motion is nothing but a straight line, right? It is in pure translation. So when it is in pure translation, you have to go and stand at the infinite distance. When you go and stand at the infinite distance, you can observe pure translation. That's what I am telling na. Please understand.
సార్ అప్పుడైనా కానీ స్ట్రైట్ లైన్ గానే కనపడుతుంది కదా, ఎందుకంటే స్ట్రైట్ లైన్ గానే ఉంటుంది కదా సార్ పర్పెండిక్యులర్ డిస్టెన్స్, పర్పెండిక్యులర్ లైన్ అనేది.
Infinite distance and can you measure it?
No sir.
What is the straight line definition? It is now
It's a number of points.
నేను ఒక ఎగ్జాంపుల్ మీకు ఒకటి చెప్తున్నా. సపోజ్ ఇఫ్ మై కర్వ్ ఇస్ లైక్ దిస్, if my curve is like this, if my curve is like this, if my curve
Increasing of radius.
if my curve is like this, ఈ అన్ని కేసులో ఏంటి, నా రేడియస్ ఆఫ్ రొటేషన్ అనేది ఇంక్రీజ్ అవుతుందా లేదా? ఆర్ వాల్యూ అనేది ఇక్కడి నుంచి ఇక్కడికి ఈజ్ మోర్, ఎస్ ఆర్ నో? హియర్ ఇట్ ఈస్ డబుల్ మోర్, అవునా కదా?
Yes sir.
So I can go at like a straight line where my radius touches to infinite. Now you got it? So sliding pair is nothing but your radius of rotation lies at the infinite distance. Okay, this is about the sliding pair. And the beauty of sliding pair or instantaneous center to mark in a mechanism is I can shift. Okay, so we can, so this is the point where in problems also I'm going to use this. The first problem which I'm going to explain you, we are going to shift this particular line. We can shift the I12 line. So at infinite distance, this is my I12 line. We can shift the I12 line wherever we need. Wherever we need. But it should be perpendicular to the direction of motion. Okay, that is the point you need to remember. So this is about the sliding pair. Now the third pair is rolling pair. So this is rolling pair. So I hope rolling. So do you remember rolling? In the first topic which we have discussed different types of pairs. So rolling pair is,
Yes, sir. Yes, sir.
yeah. So this is my surface. So this surface, on this surface I am placing a roller. So the point of contact, this is
Line contact.
yeah. So we'll see whether this is the point or not. So I'm just taking an example. So here I took an example. This is the point. So if I want to find out the velocity, so this velocity should always be perpendicular. This is the, suppose this is nothing but center of mass. So while it is moving linearly, this should be the center of mass velocity at this particular point. So what you're going to do is you want to find out this particular point A velocity and point B velocity. Sorry. Happen. Yeah. Point B velocity. So here the velocity, because the direction of motion, this is velocity of B, this is the velocity of A. So it is rotating in angular velocity in clockwise direction. So velocity of Cm, okay, so it should be equal to R into omega. So R is nothing but the center of rotation or radius of rotation into omega. So this is rotating with angular velocity. What you're going to do is you're going to draw a perpendicular line. So this is the perpendicular line. And from B also you are going to draw a perpendicular line. So these two perpendicular lines are going to join at a point. Now this point is nothing but the intersection of surface, that means floor surface, to the roller point of contact. Give me a minute.
Yes, sir.
Okay. I'm drinking water 1 minute. This is the point, what instantaneous center. So this is link 1, 2, and this is the point I12. Okay. So this is the story about rolling pair, and next is the suppose if at all it is a, this is the flat surface, na? Suppose if the surface is, it is a curved surface, how we can find out this particular center of rotation? So here I'm just drawing convex surface and concave surface. So this is convex and this is concave. And on this concave surface, convex surface, there is my slider, which is sliding, okay, or moving in this direction. So you're going to take two reference points, okay. So if you are taking two reference points, just draw a perpendicular line to the direction of motion, okay. So here the velocity vector goes like this, and here the velocity vector goes like this, these 2 points. So if you join these 2 points, okay, so it is going to intersect at this particular point. So this point is nothing but what? I12. Similarly, here also, if you can take a body and you can take two reference points and you can draw two velocity vectors, perpendicular lines to the velocity vectors, and these 2 points are going to join at one point. So this point is nothing but I12. Okay, so these are the I centers for different bodies. So I'll stop here today, and in the next class we'll discuss about Kennedy's theorem and followed by problems. Okay, So in today's class, so if you have any sort of problems, please let me know. Or is it okay?
సార్
Okay,
ఒకసారి
sir.
రోలింగ్ పేరు ఒకసారి చెప్పరా?
Rolling pair oxara. Okay, so can you see the figure?
ఎస్ సార్.
Yes. So ఇక్కడ నా reference links ఏంటంటే link number 1 and link number 2. Link number 1 ఏంటిది? Floor or the surface. So this is my link number 1, which is fixed. Okay, road surface. And this link number 2 is my roller. This is link number 2. Okay, suppose if I say this particular body is in pure rolling, okay, and this is my center of mass. O is the point, the center of mass. The linear velocity of the roller, okay, it should be in this direction. That is, velocity of center of mass should always match through the center of rotation. Okay, so if I say this is in pure rolling condition, so while it is rolling, so it is moving with some angular velocity omega, yes or no?
Yes, sir.
And the radius of rotation is say r. So velocity of cm is equal to, I can say, r into omega. సో ఇప్పుడు నేను దీని యొక్క ఇన్స్టంటేనియస్ సెంటర్ లైక్ విత్ రెస్పెక్ట్ టు లింక్ 1, లింక్ 2 ప్యూర్ రొటేషన్లో ఉందా లేదా చూడడానికి ఎక్కడి నుంచి నేను చూస్తే అది ప్యూర్ రొటేషన్ ఉందో లేదో తెలియడానికి వాట్ ఐఎమ్ గోయింగ్ టు డూ ఇస్ ఐఎమ్ గోయింగ్ టు సెలెక్ట్ 2 points on the surface of a roller. Now this is the roller, this is the point on the roller surface at point A, and I'm taking another point here at point B. So because it is rotating in clockwise direction, so here at this point my velocity vector direction will be in this direction. Yes or no? This is the velocity vector A, VA. And at this point my velocity vector at B is tangentially I have to draw. This is my VB. So somewhere it's going like this. Yeah, this is velocity of B. So what I'm going to do is I'm going to draw a perpendicular lines. Okay, perpendicular lines with respect to these velocity vectors. So this is the I'm using my hand. Some problems will be there. So okay, so this is some velocity vector. So basically ఈ రెండు velocity vectors ఏవైతే డ్రా చేస్తున్న perpendicular lines అవి ఎక్కడ మీట్ అవుతాయి అంటే it is going to meet at the point of contact between the roller and the surface. అర్థమైంది కదా? పాయింట్ ఆఫ్ కాంటాక్ట్ దగ్గర మీట్ అవుతాయి. దిస్ ఇస్ ద పాయింట్ ఆఫ్ కాంటాక్ట్. సో అట్ దిస్ పాయింట్ ఆఫ్ కాంటాక్ట్ ఐఎమ్ టేకింగ్ ఇన్స్టంటేనియస్ సెంటర్ ఆఫ్ రొటేషన్. దిస్ ఇస్ I12. అర్థమైంది కదా?
ఎస్ సార్, అర్థమైంది.
ఓకే, ఇంకా ఓకే రైట్?
ఎస్ సార్.
So shall I stop here now, both Vasu and Raghunath?
Yes sir.
Okay, thank you ma, thank you very much.
Thank you sir.
Yeah.